the horizon. So this was a kind of an old problem in general relativity. The question in vacuum was open, and some people would say that maybe it's still a little bit open. Anyway, so for these double balanced black holes I've just mentioned, as well as the hairy black holes, which are indeed the kind of constituents of this composite system, the bosonic stars play a crucial role. And this is just a point I would like to make in relation to black holes, because my talk will be mostly devoted to the solitons. So, and this is really the goal of my talk, to tell you about something about this landscape of solitons in this class of models. So I would like to tell you a bit more about these bosonic stars. And everything I'm going to say here is, well, in general relativity. So in fact, from the gravity perspective, these bosonic stars appear in general relativity. By this, I mean it's not modified gravity, albeit they are generalizable to modified gravity. So if you have, these bosonic fields that are non-minimally coupled, or you have, modification in the pure gravity sector, you can have this type of solutions as well. But these ones appear in general relativity with simple and physically reasonable matter sources, just a complex, massive scalar field or vector field, complex, massive, so a Proca field, possibly with self-interactions, but certainly with a master. So these two classical effective field theories that I'm showing in this slide stand out on a simplicity criterion, but are by no means exhaustive. The corresponding solitonic solutions are called scalar boson stars in the first case, or vector boson stars, also called Proca stars in the second case. Collectively, sometimes they are called bosonic stars, encompassing both the scalar and vector case. In both cases, the field mass parameter, mu, which you see here, determines also the maximal mass of the stars, and I'll show you how that works, and can be faced as a new scale. So often in the following, I will call this the reference model, simply because they are the simplest. But remember, these type of solutions emerge in many other more complicated models. One can also give bosonic stars a more microscopic perspective. They are often described as a Bose-Einstein condensate of many ultralight particles in the same quantum state, therefore justifying the classical description, meaning you are dealing with a system that the typical action is much, much larger than h bar. The need for ultralightness comes from the existence of a model-dependent maximal mass that I've just mentioned in the previous slide for these bosonic stars. And when I say maximal mass, I mean a maximal ADM mass. So this is the typical scaling for that ADM mass of the star, which goes as 10 to the minus 19 solar masses times the inverse of the particle's mass in giga-electron volt. Thus, for bosonic stars with masses in the astrophysical black hole range, so that, for example, they could mimic black holes, the fundamental bosonic particle must have an ultralight mass within this range that you see here, 10 to the minus 10 to 10 to the minus 20 electron volts. Now, if such hypothetical particles have feeble or no interactions with standard model constituents, they are fuzzy dark matter and likely only detectable gravitationally. Of course, a very important question is, what is their high energy physics origin? How can you have such light masses in a consistent model and protected from all sorts of corrections? So a possible origin is the so-called string axiverse, and this has been debated for over a decade now. But there's also simpler extensions of the standard model where they could appear, and that was discussed in a paper that was done here in collaboration with some particle physicists and also a group in Valencia and other places. So I would suggest you to take a look to see some possible high-energy physics models where these things could emerge. Okay, so let's look a little bit at the simplest possible solutions of spherical boson stars, or bosonic stars, to encompass both the scalar and the vector model. So the simplest ones are spherically symmetric, as you could guess. Now, when you do the ansatz for either the scalar field, which is a complex field, or the vector field, a complex vector field, you always introduce a kind of an amplitude that has a radial dependence only, but crucially, this has this harmonic time dependence that introduces the frequency small omega. And this frequency determines the mass of the solution. So you can see in these two plots for the scalar on the left and for the vector on the right, the ADM mass of the solutions in units of mu, the scalar field mass, versus the frequency of this harmonic time dependence. Now, the solutions, they fall into this red solid line in either case. It's very similar in the scalar and the vector case. So just look at the red solid line. And there's this typical spiraling shape that appears when you calculate the space of solution. Often we call it the domain of existence. And well, you can ask many questions about how each of these solutions, so each point there is a solution, it's a spherical star. How are the physical properties? Well, one important physical properties is their stability. Well, are these solutions any stable? And what has been known and for many years is that when you study linearized radial perturbations of the coupled matter gravity system, there is an unstable mode that arises precisely at the maximum of the ADM mass. These are the simplest, what's called the fundamental family of solutions, meaning they have no the minimum number of nodes for the radial function in spherical symmetry. And so what people have seen then, based on this evidence or thought, is that to the right of this maximal ADM mass solution, there's a stable branch of solutions. And then so this is from the maximal frequency until the maximum ADM mass, and then the other ones are unstable against radial perturbations. And in fact, it's known what occurs to them, to the unstable solutions when they are perturbed. Some migrate to the stable branch, some collapse into black holes, and some disperse altogether in a fission-like event. Then there's been a complete analogy between both the scalar and the vector bosonic stars in this understanding of this type of radial stability. Now, the conclusion that there's a stable branch of these spherical bosonic stars was reinforced by two other analyses. First, these stable bosonic stars, spherical ones, both in the scalar and the vector case, were seen to approximately form dynamically from generic dilute initial data. So there's a mechanism for formation. That's very important. So here's the classical illustration by Seidel and Swen from the 1990s. And this is for the case of the scalar stars, but that has been repeated for vector stars. So you start with a coherent complex scalar field with a Gaussian distribution. And one observes that under its own weight, this field, the scalar or the vector field, kind of collapses. It's an incomplete collapse. You don't form a horizon. But there is accompanying this incomplete gravitational collapse a relaxation mechanism that has been called gravitational cooling. And there is an ejected scalar field radiation. It's not really radiation because it's a massive field, but and this is carrying the excess kinetic energy away such that a more compact object can form and virialize. Thus, the evolution leads to a kind of a perturbed, more compact object, the scalar boson star, with mass below the maximal mass of the model, even though we started with a total bosonic mass in the initial data above the maximal mass of the model. And the result holds for generic initial data, albeit here we are restricting to spherical symmetry, and there is therefore no gravitational wave emission. And also because these bosonic stars, both the scalar and the vector, were seen to be perturbatively stable against spherical perturbations and to form, as I've just described, they also started to be evolved alone or in binaries, producing waveforms for at least a decade. And as an illustration, what you can see here is the first orbital merger of two spherical vector boson stars. This was done a few years ago already. These simulations were typically quite short and doing head-on collisions or with some momentum transverse to the separation so that they could get a little bit of an orbital motion and not just a head-on collision. And they are done with numerical relativity techniques, which are under control for this case, which is very nice. And sometimes people say, and rightfully so, it's even easier than fluids for various reasons. And for instance, you can use the Einstein toolkit. It's open to the community, and there are thorns now that have already encoded the equations for this type of matter content and the modified Einstein equations, well, that is with the right energy momentum tensor. So accordingly, everything seemed to agree these spherical stars in the right branch are stable. And one of the things that I would like to tell you about today is that this is not so. Well, recently we found that there is actually a very important difference between the scalar and the vector case. And this was a dynamical surprise. It turns out that the spherical vector stars, these are called mini protostars. Mini means that the potential doesn't have any self-interactions here. That these spherical protostars are unstable, but only against non-spherical perturbations. And this is, I thought, a very interesting, surprising result. It was reported in this paper here. And I would like to tell you about it. But before I discuss it, let me revisit the scalar case and tell you another feature about these bosonic stars. Unlike black holes, static black holes in Einstein-Maxwell, that we know are actually spherical by Israel's theorem, bosonic stars can have a multipolar distribution. And this was first seen for the scalar model of mini boson stars. So here's the morphology of the angular distribution, and it is essentially determined by one living real spherical harmonic. And let me tell you a way to think about these solutions, which again, they are static as a metric. There's always the harmonic time dependence in the amplitude, but in terms of the physical quantities, they are always static. There's a time-like-killing vector field everywhere. Now, the way to think about these solutions could be the following. Now, in flat space-time, the free, massive, Klein-Gordon equation admits this type of solution, where there's a harmonic time dependence, y are the real spherical harmonics, and r is a radial function. It's written then in terms of this modified Bessel function of the first kind. Now, this solution is in flat space for the Klein-Gordon equation, and it's not regular. It diverges at the origin. But minimally coupling this Klein-Gordon field to gravity and turning on gravity regularizes these solutions. And their nonlinear self-gravitating versions for the different choices of the spherical harmonic are these multipolar stars that you see here. So the last two numbers in this trio, so each next to each figure, you have a phi, a scalar field with three numbers, and the last two numbers are the L and the M of the corresponding spherical harmonic that you can see very clearly if you turn off gravity. So these here are the monopolar stars, these are the dipolar, these are the quadrupolar, and so on. And there is a clear hydrogen orbitals-like morphology. And like in hydrogen, the energy you expect is larger for larger quantum numbers, as is illustrated here for this spherical, that is the monopolar, the dipolar, and the quadrupolar families of stars. So each of these curves is the family of one type of those stars. And you see that the energy, in this case, the mass for the same frequency, goes up as you go into higher multipoles. A difference with the orbitals in quantum mechanics is, of course, that each choice of the multipolar structure, YLM, gives rise to a continuous set of solutions. There's a family of solutions which exists for a frequency interval rather than a single frequency arising as energy quantization, which is what occurs in quantum mechanics. But fixing the frequency, one clearly sees that the higher multipolar stars have higher energy. Okay, but when you try to do the same construction with protostars, you find something different. So here are the masses along the space of solutions for the spherical case, that is the monopolar stars. This is the dashed black line. For the dipolar case, which turn out to have a prolate morphology, that's the blue solid line, and the quadrupolar case, which turn out to have two separate energy lumps, which is the red solid line. And there are two remarkable features here. First, fixing the frequency. The lowest energy configuration for the frequencies where the stable branch of mini protostars was thought to be is not the monopolar star, but rather the dipolar star that has lower mass. In fact, even the quadrupolar stars can have smaller masses, energies. And this is energetic evidence that the spherical stars are not the ground state of this mini Proca family. And we were quite puzzled with this result. So, of course, the true discriminator of stability should be dynamics. We've given some other evidence for the prolate stars being the ground state, but I will not go into all the details. I will show you some dynamical results coming out from fully three-dimensional simulations using numerical relativity and the Einstein toolkit, and the machinery that was developed in previous works. See example, the one that is quoted, the second round. So we tried with this to address a number of questions. Here's the first. If the dipolar protostars are the ground state, are they stable in the long-term numerical evolution? So for testing this, what we've done was to select a number of solutions, which we identified as 1 to 4 in this slide, along the blue solid line. So these are prolate protostars, and we've evolved them. And here I'm illustrating evolutions with solution number 3. The other ones are similar. And these evolutions impose no symmetries. So you have to perform fully 3D evolutions, and this was actually a problem before. But anyway, on the left-hand side, you will see, this is going to be a movie, the imaginary part of the Proca scalar potential. Well, that's essentially the AT component of the Proca potential, okay? On the right-hand side, you see the energy density. Now, these evolutions run to around 20,000 in units of the Proca mass. So they are fairly long-term evolutions. And on the left, one sees sometimes the change in colors corresponding to the phase at which the snapshot is taken. This is just phase dynamics. On the right-hand side, we see no evolution. On the energy distribution, which you can approximately see, it's prolate, it's not spherical. So no sign of instability is found, and the same occurs for all solutions studied. So prolate protostars in the right frequency interval are dynamically robust, at least in these fairly long timescales. So we pose a second question. If the dipolar protostars are the ground state, are spherical stars unstable? And then again, we selected a number of solutions identified in this slide from 5 to 8. So this is along the black dotted dashed line. for the spherical stars, the monopolar stars, and choosing these solutions, we've evolved them. Let me illustrate again these evolutions with one of them. This is number 7, doesn't really matter. Again, on the left-hand side, you see the imaginary part of the Sproca scalar potential, and on the right side, you see the energy density, which you can see now is round, is spherical. So I'll show it. Yeah,
there's one question. Can I, if I interrupt you and tell? One body has asked, can you please clarify how the stability of the perturbation depend on the maximum ADM mass again, please, if it is just.
Yes. So we know that beyond the maximum, these spherical stars are already perturbatively unstable against spherical modes. And for the scalar and the vector case, both of them, we know the spherical modes do not exhibit any instability. What I'm trying to make the case now is that in the case of the vector, that is Sproca stars, even though there is no instability in the spherical sector, there is a non-spherical instability, which only seems to happen in the vector case. And this happens even before you reach the maximum mass solution. So all of these spherical vector stars that were thought to be the fundamental state are actually unstable, and they decay to another state, which is the true fundamental state, and it is not spherical. I hope this clarified. Yeah, thank you so much. So feel free to at any point interrupt me. And anyway, so I will show this again. So then what you're seeing here is that at some point during the evolution around 2000 or so, changes become visible. And the stars, I'm showing again, ceases to be spherical, seems to develop a prolate kind of morphology, simultaneously getting a kick in the Z direction. This supports the hypothesis that they are decaying into these dipolar prolate stars. The kick also seems to be generic, and this is related to a change in the center of mass, and there is an accompanying emission of Broca field and also radiation that carries momentum in the other direction. The decay from the spherical to prolate solutions, with the first actually being an even parity and the second being an odd parity solution in terms of the matter field, seems to turn on this momentum turn in the metric that always triggers this kick. So overall, we found that there's a rich dynamics in the model. In some simulations, we try to block the decay channel into the prolate stars by simply imposing a Z2 symmetry. So the Z2 symmetry would kill the prolate solution because the Broca field is Z2 odd rather than Z2 even. And so you impose a north-south symmetry. But even then, the spherical stars, well, they get some dynamics in which they seem to decay into an intermediate quadrupolar state and then decay into a prolate state, but oriented rather than in the north-south, in the east-west. So the kind of system finds a way to circumvent the symmetry that was imposed, although this imposition does mitigate the instability, and it seems to make it take longer to occur. Anyway, the all evidence supports that these dipolar stars are really the ground state. Now, you could also reconsider what happens if we now evolve this dilute cloud of spherical Broca field, that is this gravitational cooling mechanism of formation that we've seen before, that was done in spherical symmetry, but without imposing spherical symmetry. So you start with something which is spherical, you let it evolve, but in your computer, you're not imposing spherical symmetry. You're doing a full 3D simulation. Now, what happens is indeed that imposing no symmetries, one clearly observes in the collapse of the spherical cloud, the breakdown of the spherical symmetry. And again, hints, although these simulations never reach a final equilibrium state, of a dipolar structure, as you can see in this kind of final snapshot, oriented in some direction, in this case at 45 degrees. So our conclusion is that the Proca model in the static sector has a non-spherical ground state, and the spherical solutions of mini Proca stars considered up to now or up to recently as the ground state are actually unstable against non-spherical dynamics. So there's some comments why this was, for instance, missed before, because some of these evolutions did not actually impose too much symmetry. It's an interesting example because you are saying that staticity and stability are actually implying non-sphericity, which is like, the opposite somehow of Israel's theorem for black holes. These objects can be very compact, by the way, and that's why it's interesting. And also there are other interesting systems where spherical configurations can decay into non-spherical ones in more basic physics, if you're interested, like a charged liquid drop, which was studied by Lord Rayleigh back in the day, in the 19th century. I should also say that there were some results in the Newtonian regime that were already hinting at this the non-stability of the spherical Proca stars. But the most surprising result, perhaps, is precisely in the compact relativistic regime, because our intuition from black holes is typically that as you get more compact, things become more constrained. And if you have some static system, it becomes rounded.
Carlos, there is another question.
Please.
So the question is, it may be a nice question, but it is unclear to me what stellar topologies do the multipolar solitons correspond to physically?
Topology here is always trivial in the sense that, so topology of space-time. If you ask what is the topology of surfaces of constant energy density, say, that can be complicated and it can vary. So sufficiently in some regions and for some values of this energy density, it will coincide with your intuition of spherical harmonics, but it needs not to be so for all values of the energy density. But let me emphasize, in terms of space-time, topology is trivial, okay? So there's no non-trivial topology here. These are non-topological solitons. But of course, the morphology can be complicated. I hope that this answered the question. Otherwise, we can come back to it at the end.
Okay. Yeah, okay.
Thank you so much. Thank you. Okay, so you may be wondering, though, if this result impacts for the rotating Proca stars. Because I've been dealing with static stars. They don't rotate. They don't have angular momentum. And here there's an interesting story. Because the spherical Proca stars that I've mentioned early on that were thought to be the ground state, but they are not, they were found to having one radial node in the temporal component of the Proca potential. Now, the number of radial nodes typically is describing a sort of excitation, like in hydrogen, radial nodes of the wave function. But curiously, the spherical stars had one radial node. At least there could be more. Of course, the prolate stars do not have any radial node, and that's, again, evidence that they are indeed the ground state. But because the spherical stars initially were found with one radial node, the rotating stars that were initially constructed, they also had one radial node. And they had this Saturn-like morphology that you see here for constant energy density surfaces. But later, triggered by different motivation, the rotating Proca stars, without any radial nodes in the temporal component of the Proca potential, were actually found. And this seemed very surprising at that time because, the rotating stars didn't have any radial node, but the static stars, the spherical ones, had one. So why wouldn't the static sector have a no radial nodes? And the answer was, well, it does have no radial nodes, but you have to go away from spherical symmetry. And now we know the answer. These rotating stars, Proca stars without radial nodes, they are still believed to be the ground state of the rotating family of solutions. And in fact, they are known to be dynamically more robust than the spinning scalar stars, which are toroidal. instead of spheroidal. In fact, when the boson stars, the scalar boson stars, were first found in the 1990s, they were called a mass torus in general relativity. But they, again, were, not much was known about stability all along the space of solutions, even before the maximum ADM mass. But it was found a few years ago that these rotating scalar stars, all of them in this mini model that is without self-interactions, they are all unstable. They break down against a non-axisymmetric mode. So this I can show you in a little, again, movie. So what you see here is the visualization of a fully nonlinear evolution of the Einstein-Klein-Gordon system in the left panel. The color code denotes the scalar field amplitude. So you see, you're seeing it from above. So you see it's a toroidal thing. And at some point, which is a moderately long time scale of the order of 1,000 light crossing times, there's a non-axisymmetric instability that kicks in, and an apparent horizon forms. You can see that in the right panel, where the mass associated to this apparent horizon is this blue solid line, and the energy associated to the scalar field is the green dashed line, which tends to vanish as it is swallowed by the black hole, signaling that there is indeed the black hole formation. So these stars, rotating scalar boson stars, all of them, they are unstable, even the ones that would be or are in the tentative stable branch. There is no stable branch here. But this instability seems to be absent in these cousin Proca models. So the spinning Proca stars without any radial nodes, they seem to be dynamically robust. And this was supported by numerical evolutions with a timescale at least 10 times greater than the ones where the scalar instability is seen. So as illustrations here on the left panel, one starts with a spinning Proca star with a very strong perturbation that visibly changes its energy distribution. And then on the right panel, one starts with an excited spinning Proca star that has an energy distribution which is Saturn-like. And in both cases, the evolution approaches a spheroidal fundamental spinning Proca star without shedding away of the angular momentum, or all of it, and without collapsing into a black hole. So the conclusion is that spinning Proca stars are dynamically more robust in the simplest models, that is, without any self-interactions. The addition of self-interactions has an important impact on these conclusions, but I will not discuss that too much today. But for instance, in the scalar case, it can mitigate the instability and bring new regions where stars could be dynamically more robust. So to summarize, although the scalar and the vector boson stars have a clear parallelism in the existence of solutions, dynamically a surprising different picture emerges with the solutions selected by dynamics being quite distinct. So in the scalar sector, we have a spherical ground state that's dynamically robust, and there are dipolar solutions which decay, and the rotating solutions also seem to collapse. But in the vector sector, the spherical stars are not the ground state, it's a dipole, and the rotating solutions, which are spheroidal, are also dynamically robust. So it's very interesting to observe these differences, and there are probably deeper reasons for this, which one could discuss. But let me conclude this part on this discussion of bosonic stars by saying that the models that I've been discussing so far are single field. So you consider in the scalar case a single complex scalar field, or in the vector case a single complex vector field. But this single field bosonic stars can be used as building blocks for multi-field bosonic stars, constructing appropriate superpositions, which moreover can also change the dynamical properties. So for instance, it's known that excited monopole scalar boson stars, which excited means that they have radial nodes, this is in the scalar case, They are unstable against the decay into a fundamental spherical boson star, which has no radial nodes. It can be stabilized by adding a sufficiently large fundamental monopole boson star as a second field. So you build a kind of a hybrid state, and you stabilize the excited part. And in the same spirit, for the non-relativistic bosonic stars it's called the Schrödinger-Poisson system. This is the non-relativistic version of what I've been discussing. A dipole configuration is stabilized by adding a sufficiently large fundamental monopole. And these examples turn out to be illustrations of a stabilization mechanism that was discussed in this paper that I put here at the end, discussing also families of multi-frequency, multi-field bosonic stars. So this triangle that you see in this illustration is for a so-called L = 1 family, which has 3 complex scalar fields. And depending on the relative amplitudes of these 3 complex scalar fields, you have different limits. For instance, you have a dipolar limit. You have also a limit where you have the single field kind of spinning stars that could be spinning in either way. And you also have an interesting limit in which all the 3 fields have the same amplitude, but they have different spherical harmonic kind of angular dependence. And you build these so-called L boson stars, which turn out to be spherical, even though the individual fields, they have some non-spherical morphology independently, but they combine themselves in a way in which the end product has a spherical morphology. So this is only one example of one such family. And this is for the scalar case. Recently, people have been doing this also for the vector case. It's possible to build also these, say, L Proca stars. And there's a lot of things to explore also on how these combinations can change the dynamical properties of this type of objects. So in the remaining time of my talk, I would like to tell you a bit more about phenomenology of these bosonic stars. And I would like to focus on the ability to mimic the phenomenology of black holes with current data, which I would like to call the imitation game. So I would like to give you 2 examples. And well, let's see how time goes. But the first example is related to gravitational waves. I would like to discuss the ability of bosonic stars to mimic a particular event, which is GW 190521, which was a very particular event. You might have heard about this. The progenitors in this event were estimated when it was announced as the most massive of any event thus far, about 85 and 66 solar masses for the 2 progenitors. And this means that within the uncertainties, at least one of them is in the so-called parainstability supernova gap, which is a part of the mass spectrum of black holes where, it's not expected that such a black hole could be the direct product of the core collapse of a neutron star, and because of the properties of the supernova. So this leaves the question of how these progenitors came to be. Because even if it was a black hole, it was not an easy to form black hole by just this process. It could be, of course, a result of a merger, and people have speculated about that. And because it's a very massive event, it is a low-frequency gravitational wave signal, so you only see the very end of it in the current detectors because of the sensitivity band. So there is no in-spiral in the observed transient. And this leaves room to speculate about the true nature of the event. In fact, the event looks as much as a simple burst-like transient as the final part of an in-spiral, because it misses the clear chirp track that you see in those longer events where you have a few orbits. So this odd event is an invitation for alternative explanations, and one was proposed in this paper that we put out already a couple of years ago, where we analyzed this as a collision of spinning Proca stars. And doing a likelihood Bayesian analysis using the same libraries as the collaboration, the LVK collaboration, used for black hole binaries, plus an extra library of waveforms for Proca star collisions, which I'll tell you about, gave a slight statistical preference to the Proca model. Furthermore, this analysis could determine the mass of the putative ultralight vector boson that was the composite particle, the particle that was composing these protostars, and gave a value of 8.7 times 10 to the minus 13 electron volts. So my point is that even if one completely rejects any physics reality of this scenario, the analysis illustrates the path from an exotic theory to real observation. So let me tell you how this was done. Given the dynamical robustness of the spinning protostar that we discussed, so here I'm doing spinning protostars, the ones that I told you they are dynamically robust. They can be collided in binaries. Now, the simplest such collision are head-on collisions. Considering this over, quasi-circular mergers is, of course, just the first step. It has technical advantages. And one may argue this is less astrophysical, which is true. But the point to be made here is that even then, the model can compete with vanilla black hole binary mergers used for GW190521. So the simplest setup is this one that I'm illustrating here, which can be then generalized in many ways. You consider two equal mass m and equal frequency omega, perturbatively stable spinning vector bosonic stars. The spin axes are aligned. They are perpendicular to the screen, pointing towards each one of us. They are initially at the coordinate distance d in the x direction. They could have velocities vy in the opposite y direction, but here we take this to be zero. This is what is called a head-on collision. Quasi-circular binaries require sufficiently large vy. Now, with this setup, fully nonlinear numerical relativity evolutions of the Einstein Proca system can be performed. So the bosonic stars, Proca stars in this case, have an eccentric trajectory due to frame dragging because they are rotating. So there's a frame dragging, so they don't actually collide head-on. They acquire a little bit of an eccentricity. Then they merge, and there's an apparent horizon that forms. So a black hole is formed within with a certain mass, MBH, and a certain non-zero total angular momentum, JBH. In the simplest collisions, the two stars are equal. So in particular, they have the same frequency in this harmonic time dependence that we saw, and the same mass. And we can then extract the waveform of the collision process. So if we vary then the stars that we take as the initial data, the waveform varies. And so I'm illustrating here a simple scanning of the parameter space as we vary the initial stars, which we label by the frequency omega, to be the ones indicated by the red arrow. The waveforms of the collision process, as described before, they also vary, which is shown in the upper panel. And in this scanning, we do not go to too high frequencies, otherwise the final object is not a black hole, and the signal is not compatible with GW190521. And these examples are also for equal mass here. But we've also performed unequal mass collisions. And this is illustrated here in this slide. There's 4 different movies of waveforms, show how they vary when different initial data is considered, when different colliding Proca stars are considered. So the first top movie, top left, is the same as in the previous slide, and the other 3 are for unequal masses. While in these equal mass collisions, L equals M equals 3 is almost completely suppressed, the mode, compared to the dominant quadrupolar mode with L equals M equals 2. In unequal masses, it can have a significant contribution, and that's what is being shown in red. So that's another mode. And these waveforms can be now used for gravitational wave analysis, data analysis, for injections, waveform reconstruction, parameter estimation, and potential searches as well. So there's a catalog with about 750 waveforms that was constructed already, all of these from numerical relativity evolutions. And potential searches is precisely what we did with GW190521. So we can then study statistical preference using a Bayesian analysis, and this was done in the paper that I've shown you. This was led by Juan Calderón Bustillo, who's also a member of the LIGO Virgo Cagra and participated in the same analysis for LVK, for the standard interpretation of the event. And looking at this log base factor, there's different priors here, but I don't want to get into any details. The conclusion is that the base factor is slightly or even considerably better for the PROCA model. Also, the best fits is given for the PROCA model. This statistical preference is by a factor of 2 to 30, so it's not too significant. But one can say that at least there's a degeneracy, and this is the point that we want to make with this imitation game. Of course, any further conclusions have to be taken with a lot of caution. But okay, following up on this, the statistical analysis gives us a probability distribution for the frequencies of the PROCA stars, which nicely fades out at the extremes of the range we've analyzed, which suggests we are in the right frequency range. And this gives a frequency distribution centered around a particular value. And this determines the m times mu of the PROCA star, the mass in units of the PROCA field fundamental mass, let's call it. Then if you identify the mass of each PROCA star as half of the mass of the final black hole, which is reasonable here because the inelasticity is very small. So the energy lost is in gravitational waves, its fraction is much lower than in spiral. So this determines then the mass of the ultralight boson. And so you can get this type of histogram for that distribution, which is centered around a particular value. So this...
you have 5 minutes.
Okay, so I think I can finish this part, not tell you too much about the remaining, but then in questions. So to conclude using this PROCA model, we can use this event, real data, GW 1905-21, to infer the mass of the ultralight bosonic particle, which in this case is a vector particle. And this proof of concept shows how there can be degeneracy in real data between two very different models. But in order to see it, you have to do detailed phenomenology of non-Kerr models, because the searches are very much, based on having templates and therefore well-developed theory. And in this particular case, you can also get how much, you can also illustrate how you can extract physical information about a new fundamental particle, putative dark matter particle, from the data, making your gravitational wave detectors into a particle detector. And that would be, of course, a much more exciting possibility to have this type of scenario finding new physics. But a potential confirmation will require, of course, much more events, many more events, and future population studies, which are, I would say, possible within the next few years, and potentially a hint towards dark matter. So let me just finish this by telling you about a question of scales. You may be asking, so why not the other gravitational wave events? Why could this event be such a PROCA star collision and not the other gravitational wave detections? Well, as you may remember, the mass of the ultralight bosonic particle determines the maximum mass of their corresponding stars. So in this case, this turns out to be about 173 solar masses. All other events prior to this one, they corresponded to final smaller masses. So since the other events are compatible with black hole formation, with the evidence of a ring down, these cannot be PROCA star collisions. For the PROCA star collision to form black holes, they have to overshoot this limit, which was only observed at least until this event was reported by this event. And this is interesting, again, as a proof of concept to illustrate how a new scale can impact on data. Of course, this could be now repeated for other events. There's some other events that have appeared that this analysis has been repeated, and we've reported it in a subsequent paper. Now, I don't think I have much time for what I would like to tell you about the imitation game with shadows. So I can keep that for a discussion if necessary. I would like to say that, of course, there's this other observable called the black hole shadow that we take as evidence of, black holes. But again, these bosonic stars give us interesting examples where we can have interesting degeneracies, given also the limited information in the current data. And this could come from several different sources, different physical properties of the, say, geodesic motion around the bosonic star. I had two examples, one related with the fact that time-like circular orbits around the bosonic star can have a property that you do not see in black holes, which is the existence of a maximal value for the angular velocity attained at a certain radial distance. And this could actually give rise to some an effective shadow, and I can explain afterwards if you'd like. And the second thing is, if you have something that has a non-trivial geodesic structure, and for instance, this is an example where you have different disconnected regions in the space-time where there can be circular time-like geodesics and gaps between them, and this occurs also for dynamically robust Broca stars, you could have, if an accretion disk accumulates in those regions, features that again imitate, observations of a black hole. So this was very brief. I would like to just conclude by telling you that bosonic stars illustrate theoretical possibilities of dynamically robust black hole imitators that could manifest themselves only at some specific scales, and that producing detailed phenomenology will constrain the model and the corresponding exotic physics, or in the best case scenario, provide a smoking gun to this new physics. So with that, I will conclude, thanking you very much for your attention.
Thank you, Carlos, for an excellent talk. And I believe everybody enjoyed the talk a lot. So now we have 10 minutes for all the questions. So people can ask the question. People can raise their hand and ask the question, or people can also write in the chat box and I can tell the question to Carlos.
Thank you.
Yeah, Shubhodhi, can you ask?
Yes, yeah. So thank you for the talk. I just have one question, that since you mentioned the string axiverse thing, so there people just talk about about gravitational atoms, that is how a massive scalar perturbation can grow due to a superradiant instability. So if I understand correctly, that is different from this boson stars, right? Because gravitational atoms can still have an event horizon and such.
Thank you very much for your question. Yes, that's a very important point, and I would like to clarify. So when people are looking at this, they are looking in the test field approximation. So they are not really back reacting on spacetime, first of all, and there's a good reason for that. The second thing is that they are interested in these growing scalar fields or bosonic fields around the black hole, then actually decaying via the emission of gravitational radiation. That occurs if the scalar field or the vector field is real. There's a very important difference. I'm talking about complex scalar fields. So when they grow, the configuration is axisymmetric. So it does not decay that mode by emission of gravitational radiation. When the real scalar field grows, then it's not axisymmetric. It will have actually an azimuthal dependence. It will be like a bar, and this will decay via the emission of gravitational radiation. So this depletion of the cloud by this emission is then what people have argued that should be seen as a background by LIGO, Virgo, Kagra, that has not been seen, and therefore you put constraints. But the phenomenology that's being assumed is that of a real field. So again, if you have then this complex field, as it grows, you really get to a stationary configuration. So the clouds that you get from the real case and the vector case are different. There's a much more complicated story because this is just the leading mode. As you know, if you've studied these papers on these gravitational atoms, then there's another mode that grows. They have complicated interplays. So here the question also applies to the complex fields. So you have this leading mode that grows. It's axisymmetric, so it will not per se decay. But then there will be more modes that take longer to grow. And once they are starting to grow, they then will interplay with the existing mode. And because there is interference, this will lead, in principle, although the phenomenology has not been worked out in detail, to the decay via gravitational wave emission. But, what happens in detail, we don't know. But now there's a question of timescales. How long does that take? So if that would be for solar mass black holes, in fact, you could have something that's pretty fast and that could have clear signatures, which again have not been worked out in detail. But if that is for supermassive black holes, what happens is that the leading mode, if you're talking, say, about 10 to the 9 solar mass black hole, the leading mode could have a few million years. And the subleading mode can have a growth time of a few billion years. So the object that you get just from the growth of the leading mode is something that is fairly stable, even in a cosmological timescale. Now, does it back react strongly on the space-time? One of the things that we know is that from superradiance, you will not extract more than about 10% of the energy of the black hole into this cloud. 10% is not very much. It's also fairly diluted. So maybe it's not actually back reacting a lot and the test field approximation is valid. But 10% of a 10 to the 9 solar mass black hole is a very considerable amount of mass. And for instance, in the shadow, it has a very non-trivial impact that may be for the scalar case. We've done a couple of papers about this. Maybe for the scalar case, at the moment is indistinguishable from the data because there's an error bar in the measure of, the emission ring of about 10% anyway. For the pro case, it's a bit more delicate because we found that it could be a bit more sensitive. So in the future, the next generation Event Horizon Telescope and so on, this could be in principle disentangled. Anyway, so going back to your initial question, there's a different phenomenology. This is the point I would like you to take home, most important point. There's a different phenomenology if the field is real versus if the field is complex. And for instance, these bosonic stars, the solitons that I've described, they occur for the complex field. There's a similar type of lumps for real fields. They are called oscillotons. But they are not, strictly speaking, stationary or static. They actually decay. They can decay very slowly, but they decay. So there's also, in terms of exact solutions or, of solutions of the full nonlinear system, also a difference. Anyway, so I hope that I've conveyed the kind of information that was clear. If not, just please.
That was fine. I just have one related question. So for this boson star configurations, have people attempted to study their quasi-normal mode spectra? And I ask this because I am confused about what boundary conditions to apply at near the boundary of the star, because the boson cloud is spread out, right? And can these configurations have late time echoes?
Can they have echoes? Is that what you're asking?
Yeah, the echoes, and what is the boundary condition that one applies near the star surface if one is interested in doing it?
Yeah. So the echoes question, I believe so. If some of them have light rings, and I believe that in the original work, after the paper by Pani, Franzin, and Cardozo on the echoes, because the light ring was not really a probe of the ring down was not a probe of the horizon. I believe that this was worked out. If you see some papers by Cardozo, Pani, maybe Anuli collaborators, they actually analyzed some families of boson stars with light dreams to see the echoes. So boson stars don't have a surface. That's the thing one should understand, because there's an exponential fall off of this field because of the mass term. It's a Yukawa type of decay. So they don't, strictly speaking, have a discontinuity of, say, the radial pressure like a normal star. So on the one hand, this leads to a certain ambiguity in defining where the surface is. People typically talk about an effective surface where 99% of the mass is encompassed within. Some other people use, 99.9, whatever. But it decays very fast because it's an exponential decay. But on the other hand, as an advantage, the fact that there are not these discontinuities, it's a field that's everywhere kind of smooth and decaying very fast. It is much better for dynamics. So you don't impose any boundary condition at the surface when you want to calculate these perturbations. You impose a boundary condition of regularity at the origin for your modes.
Yes, thank you. And just a small question, and I will.
No, Subodhip, now we are actually running out of time. I think we're already for the next talk. The time is there. So if you have some questions, maybe you can ask later, because the next speaker is waiting. So let us thank Carlos again for his wonderful talk.
Thank you very much, and for the questions as well. I hope all is clear. If not, feel free to send me a message, an email. Yeah. I'm very happy to discuss with everyone that's interested.
Yeah, thank you. Thank you, Carlos.
Once again, thank you very much. I apologize for not being able to stay, but I have to go to Sudipta's talk. Sure. Okay. And I hope that the conference goes well, the rest of it. Thank you very much. Bye-bye then.
Thank you. Bye. Bye. So, Srijit, the next speaker is Lavinia is here.
Yes, I just have sent one message to Lavinia. I could not spot her. So let me see if she has joined or not. I have just sent one reminder.
No, her name is not there in the.
Yeah, I mean, I could not find her, spot her. So let us see. I mean, 1 or 2 minutes.
Yeah. She had the schedule, fine.
Yes, yeah, we have sent all the speakers the link, etc. So
the timing was confirmed with her fine. Bridget?
Yeah, I think she has some confusion. I just communicating with her. Probably
Okay.
let us see.
Recording stopped.
Hi, everyone. Can you hear me?
Yeah.
Hi. Yeah.
Okay, I'm so sorry.
Actually, so there was a confusion regarding Zurich time and CET. So I now understand. She
Yes,
thought
I
that
think in
it's,
the
yeah.
in the schedule it was like Central European time plus 4:30, and I thought the meeting starts later, and very sorry about that. But I am ready. I can start.
Yeah. Sure.
Thank you.
Okay. Okay, everyone. So our next speaker is Professor Lavinia Heisenberg. So she is now a professor at the Department of Physics and Astronomy in the University of Heidelberg, Germany. And she has various research interests, mostly in the effective field theories, applications in cosmology, especially in modified gravity models, testing theorems, or testing gravity theories with gravitational waves, geometrical manifestation in gravity. So today, she will be speaking about balance laws as test of gravitational waves. So yeah, Lavia.
Thank you very much for having me here. I think you have to enable me to share screen.
Recording in progress.
Okay, just a moment. Srijit, can you check?
Yes, sure. Yeah.
Okay, I think now I should be able to share my screen. Okay, I hope you can see my slides.
Yeah.
Okay, perfect. Yes. Okay, thank you very much. In case I'm a little bit late with my talk, please feel free to interrupt me. I can also finish sooner. So yes, I wanted to talk about using balance laws to test gravitational waveforms. If you are interested in this subject, you can have a look at this pedagogical introduction into this subject. There I give really very easygoing introduction about all these concepts and how we can use balance laws to test gravitational waveforms and directly actually also the gravity theory itself. Okay, so let me then start. As you know, when we talk about gravitational waves, the main progenitor is like the main objects are the black holes, and so what are black holes? We all know black hole is a region of space-time where gravity is so strong that not even light can escape, and this is a direct prediction of general relativity actually. And so more mathematically, the Schwarzschild black hole is a vacuum solution of Einstein's field equations, which satisfy certain criteria that is applied to isolated system with the cosmological constant being 0 and spherical symmetric space-time and static space-time. So satisfying this condition, you can then get the Schwarzschild black hole solution. And so what you have to impose is basically that your metric satisfies certain conditions, that the Lie derivative associated to time translations and rotations vanish. And so the first condition is the stationarity, that it means that you have a time translation invariance in your background metric. And the other ones, as I mentioned, these are rotational symmetry. And so when you impose these conditions on your metric, then your metric has to have this very specific field configuration. As you can see, only certain components survive and they have only R dependence. And then you can insert this ansatz to the Einstein's field equations. And in order to solve these equations, you have to introduce further conditions actually, namely very specific boundary conditions. And one specific condition is namely that the spacetime is asymptotically Minkowski, meaning that if you go at far infinity, your metric should mimic Minkowski. And the second condition that you have to impose is at this far infinity from the source, we should recover Newton's law. And this fixes the coefficients of your Schwarzschild solution in this very specific form. And these boundary conditions do not completely fix the solution, actually. We still have gauge freedom. And different gauge choices might give rise to different looking solutions. For instance, the Schwarzschild gauge, in that case, the metric ansatz looks in this very specific way. You could also choose a different gauge, like this one, for example, where naively you see that there is this off-diagonal term, but nevertheless your static spherical symmetric solution is imposed. Okay, so even though these solutions look different, they are physically exactly equivalent, and they agree on all physical predictions like gravitational redshift, time dilation, bending of light, existence of event horizon. But you have to go through these steps. Imagine you change your gravity theory. It's not general relativity anymore, but something else. You have to go through these steps that I just introduced here. Okay, and one important theorem is the Birkhoff theorem, which states that any spherically symmetric solution of Einstein's vacuum field equations is necessarily, in order to have Schwarzschild solution, in particular, it is static. And the important consequences of that is that spherically symmetric pulsating stars do not emit gravitational waves. So this fact follows also from the quadruple formula. So if you want to have black hole solutions, as I was telling you, you have to satisfy certain conditions, assumptions, and then depending on the properties of the considered matter or object, you can have different type of solutions. For example, you can have Schwarzschild solution where you have only the mass of the black hole. You can have Reissner-Nordstrom solution. If this black hole is also charged, then you have the associated charge. Then you can have, rotating solution. If this has also angular momentum, this is the Kerr solution. And it can also have all of them at the same time. So it can be charged and rotating. Then you have Kerr-Newman solution. And so one very important theorem within this different black hole solutions is the No-Hair theorem, which basically states that all stationary black hole solutions of the Einstein field equations coupled to the standard model matter field are completely characterized by only three measurable parameters, which is given by mass, charge, and the angular momentum. So when two black holes merge, the system is highly non-spherical and non-stationary, and therefore the No-Hair theorem is broken. And because of that, you have the hope to then emit gravitational waves. So if you have just a single black hole boring sitting there, you will not have gravitational wave, and therefore you really need to have a merging of two stars in order to break the spherical symmetry and to break the stationarity. Okay, so here is two black holes, right, merging together. And as you can see, it's highly non-spherical and highly dynamical. And due to those two effects, we are able to emit gravitational waves, and we have the hope to actually measure these gravitational waves. Okay. So then let me introduce gravitational waves in a nutshell. So gravitational waves are ripples of space-time, and they give rise to changes in lengths and shapes. Nevertheless, it's not so easy to measure these changes because they're really super duper tiny. As you can see, 10 to minus 18 meters. Nevertheless, we are now able to measure them. And now there are important questions when we observe gravitational waves, like how do we extract information about the masses of the binary system? And how do we know the distance and the location in the sky of the binary system? How do we determine the total power emitted, and how can we test different theories of gravity, if it's GR or something else. And the answer to all this question is gravitational waveforms. Maybe at this point, could you remind me how much time I have? So that I just know.
Yes, just one moment, please. I think we're close to 20 minutes.
The total amount is 20 minutes?
I will just clarify that.
No, I mean, you have at least 40 minutes.
Yes,
okay.
40 minutes, huh?
Okay, good. Because, I'm giving a little bit long introduction. I wasn't sure if I should hurry and make it quicker. Okay, so in order to answer these fundamental questions, the big answer basically to all of this question is gravitational waveforms. So, as you can see here in this visualization, you see there are like different black holes, different objects involved, and depending on their masses, you see these wiggles, they look very different, right? And so by observing these wiggles, which is the gravitational waveform, you can try to extract all the information about the masses, their distances, their inclination, so the parameters involved, the theory of gravity. Yeah, so everything, all the physical information is encoded in these wiggles. And our task as physicists is basically to understand these wiggles and to theoretically predict these wiggles and then compare these wiggles to the observed wiggles and see how the parameters match together. Okay, so far so good. Here is one very particular example where you can see the strain of the gravitational wave plotted with respect to time. And this is this typical waveform, these wiggles that you can see. And as I was mentioning, all the information is encoded in this wiggle. And for example, from the frequency evolution, you can infer the involved masses. From the amplitude and the inferred masses, you can infer the distance. And from the time of arrival, the amplitude and the phase at the detector, you can infer the sky location, and so on. This is just to give you an example. Okay? And in standard general relativity, you have these two strains, these two polarizations that you can measure. Basically, they are called H plus and H cross. And they can be visualized by the way how they change test masses. So when there is a wave with this type of polarization, how does this test masses change? And here you can see for these two different polarization and waves, you see that the H plus does this movement and the H cross does this movement. And you can extract all the necessary physical information from these two polarizations. If you had another different metric theory, another different metric gravity theory, of course, on top of the standard tensor polarizations, you might also have additional scalar polarizations or additional vector polarizations. Okay, in general relativity, as I was saying, there are only these two tensor polarizations. Okay, in order to get this waveform, theoretically, right, you have to now come up with a prediction, with a theoretical prediction. And in order to have your waveform, you have to solve Einstein's field equations. But they are not so easy to solve, and it's very highly non-trivial. And because of that, what one typically does is one looks at the different parts of this merger event and uses different theoretical approaches to calculate the waveform. For example, at the initial phase, when the two objects are sufficiently far away from each other in this inspiraling phase, one uses the post-Newtonian approximation, it's basically perturbation theory, in order to get your waveform. But at some point, these two objects come too close, which is basically the merger phase. And there you cannot use analytical methods anymore. You really need to do pure numerical relativity approach in order to get this Wiggles, this waveform. And then once the objects merge and you have your final object, which is the ring down phase, you can then apply again the perturbation theory, and it's much easier to do the calculation. But as you can see, you have these three different phases. And in order to get the full waveform, you have to now glue together these three different phases and match them in a correct way. And this is really very, very difficult. And you will introduce a lot of mistakes and errors if you are not careful enough. Okay. As I was mentioning, these three phases of waveform require very different approximation techniques. So post-Newtonian approximation for the inspiring phase, numerical relativity for the highly nonlinear merger phase, and then perturbation theory again for the ring-down phase. To get the full waveform, it is necessary to combine these approximated phases together into a so-called waveform model. Okay, this is basically what you have to do. And there are many different waveform models, okay, in the literature. And I'm giving here some list. This is please not exhaustive. So if I don't mention your favorite waveform model, please excuse me. I'm just trying to give you examples. For example, there are these SXX waveform models. Then there are these pure and hybridized NR surrogate models, effective one-body models, and some phenomenological models, and many, many more models derived from them. And they all use different techniques and approximations in order to get the waveform. So, as I was saying, discussing these models in detail or to discuss all of the existing models is outside of the scope of this talk. So what is important to us is what these models have in common and what distinguishes them. So because as I was telling, waveform models are really the essential tools in order to be able to detect gravitational waves and also for parameter estimation, we really need to investigate them in very much detail. And as I was telling you, each model uses different approximation and different theoretical approaches, and therefore they will introduce different parameters as well. And each model typically depends on 10 intrinsic parameters and 4 extrinsic parameters. For example, as intrinsic parameters are the true masses of the involved objects, the individual spins, the eccentricity of the orbit, the orientation of the orbit, and so on. And extrinsic parameters are like the luminosity distance from the source or the parameters determining the orientation, and so on. So you have your waveform model, which uses a very specific approximation and specific parameters. And you can then take this model and compare to observation and first of all, use that as a detection of gravitational waves and also use that as parameter estimation. And each model makes simplifying assumptions, so they are not 100% exact concerning the physics involved. So examples, effective one-body models assumes a small mass ratio of the binary, and many of the older, at least older models, they, for example, neglected completely the gravitational wave memory effect and so on. So sometimes these models can really even lack very important physics involved in these mergers. And another very important point is that each model needs input from numerical relativity for the merger phase, but numerical relativity simulations are really very expensive. Therefore, one can only cover finitely many points in parameter space, and also each model needs to interpolate between these NR data points. So you have only a few points in the parameter space, and then you have to make interpolation between these points. And each approximation technique introduces errors, and these errors can then propagate through your waveform. And so you have to understand how much error you are doing. And so given that waveform models play such a crucial role in first detecting the gravitational wave events and in extracting information from the signal, we have to ask some very crucial questions. So, for example, which of the many models can we trust when we're analyzing observational data? And which models is the closest to what full nonlinear GR would really predict for the physics of the compact binary coalescence? So if you had the perfect universe where we had the infinite amount of computational tools, what is the closest to this full nonlinear GR prediction? And can we test which model makes the smallest error and provides the best approximation? And the answer to all this question is yes, we can use the so-called balance laws. And so let me then introduce what these balance laws are. Understanding how gravitational waves are described in the full nonlinear theory opens the possibility to develop exact mathematical tests for waveform models. These are these balance laws. So these are really mathematical tests that you can apply to your model. This is, for instance, a recent idea based on this paper here. If you want to have a look on this pioneering work, please have a look at this very nice paper. So the idea, let me give you the idea behind the balance law, is very simple. So binary systems lose energy because they emit gravitational waves, and the total energy loss has to be balanced by the total energy carried away by the gravitational waves, right? This makes total sense. And this balancing of energies allows us to test and compare different models. So as I was telling you, in order to maybe have a more pedagogical introduction, you can have a look at this paper here. I would like to use this opportunity to introduce first mechanical balance laws, just to really rigorously explain to you the concept behind the balance laws, and then we will exactly use the same analogy to more complicated nonlinear general relativity. Okay, so let's illustrate this idea in more detail using a mechanical analog. And imagine you have a dissipative mechanical system. Doesn't matter, it could be a relativistic or non-relativistic system, maybe two balls, right, interacting in a specific way in this mechanical system. And now imagine you put a specific boundary around this system, which is here given by this red line. And then there will be some energy influx into this system and some energy outflux out of this system. And the energy, of course, is not conserved in this system. The system is losing energy. But nevertheless, the total in-out flux of energy has to balance the total gain and loss of energy in the system. Okay, so the energy that enters into the system has to be balanced by the energy or gained or lost that goes out of the system. So imagine we measure the energy of the system at some initial time and some final time. And therefore, the measurement will yield some specific energy at this initial time and some specific energy at the final time. And now we can prove mathematically exactly that the difference between the final energy and the initial energy is given on the right-hand side by this expression, which is basically the time derivative of your Lagrangian associated to this system, and then you perform this integral. Okay, so on the left-hand side, you have the total energy gain and loss of the system. And on the right-hand side, you have the total energy in and out flux through your boundary of the system. And this total energy in-out flux is measured by the integral over time derivative of the Lagrangian. Okay, so this mathematical law allows us to test approximate solutions to complicated equations of motion. So the strategy is as follows. Derive equations of motion from your Lagrangian, make simplifying assumptions or approximate equations and solve them either numerically or analytically, depending on whether or not it's too difficult. And then plug this approximate solution into this unapproximated, unsimplified balance laws. And then you will see the amount of error you made by your approximative solution. And the better the balance laws are satisfied, the better the approximate solution describes your full, correct physical situation. Let's give me an example. Imagine you have a rolling ball with friction. So consider a ball here sitting, and it rolls down this half pipe with friction. And for simplicity, we will assume that this ball is just a point particle and there is no air resistance. And so the equations of motion are still nevertheless nonlinear and given by these equations. As you can see, because of this term here, the equations are highly nonlinear, which makes them a little bit harder to solve. And this term here is the friction term, and this term here is the nonlinear term, which makes it difficult to solve. Therefore, we can make, for example, a small angle approximation, and then this becomes linear. And then we can see with this approximate small angle approximation, can we find simple solutions? Of course, we can find them. So this is, for example, one analytical simple solution here for this angle, which is given completely analytically based on this linear approximation. And then we can now take this and then see, actually, it describes more or less nicely the physics going on, how this ball drops down here. Now, of course, the question is, how good is this approximation? How well does it describe the previous full equation, which was highly nonlinear, right? So we plug this approximate solution into the unapproximated balance laws and plot the situation. So here is an example. Here is the energy difference with respect to the angle involved, this angle parameter. In red is the left-hand side of the balance laws, basically the energy difference. And on the blue line is the right-hand side of the balance laws, which is basically the in and out energy flux through your boundary. And the yellow one is the ratio between them. So if your solution is physically 100% correct, then this ratio between the left-hand side and right-hand side should be 1. And as you can see here, only for small angles, this approximate solution is good and your balance law is satisfied. But as soon as you go to larger angles, this approximate solution is not correct anymore and your balance laws are not satisfied. Okay, so approximation good only for small angles, which we were expecting anyways, but this balance laws really gives you a way of seeing how much error you did. Okay, So for each parameter value, you can then test how this balance law is satisfied. And for certain values involved in your approximate solution, the balance law will be satisfied in a certain way. Okay, so here, for example, for a different change value of the parameter, approximation is still good, but worse at this point in parameter space. Okay, now I would like to go from the mechanical to the more complicated general relativity balance laws. As I said, you can have a more detailed exposure here from this article. I will try to use the remaining time to explain the idea now behind the balance laws in general relativity and how we can use them in order to test waveform models. Okay, so we can apply the same ideas to general relativity to compare and improve waveform models, determine which model performs better in which region of parameter space. And in order to do that, so let's remind ourselves that balance laws are really exact mathematical relations of a theory without no approximations, right? And to develop balance laws for coalescing binary system, we need to understand gravitational waves in the full nonlinear theory, which is a highly complicated subject on its own. A detailed introduction you can find here in this notes here that I am showing. And as I said, I will not be able to give you all the details here. It's quite cumbersome and very lengthy, but nevertheless, I will just try to introduce you the important concepts. Okay, so we consider a binary system of compact astrophysical objects, two black holes, and we choose our coordinate system such that in the different path, the observer is at rest relative to the center of mass of the system. And due to the emission of gravitational waves, now there is an outflux of energy. And we can then, we can then use the signal in order to so we can then mimic that the signal is measured at far infinity, which I am depicting here with the detectors. And the signal allows us to determine certain physical quantities, for example, the kick velocity. So when the two objects merge, the final object can get a kick. This is given by this kick velocity here. And then the total mass of the binary system is a measurable object from the signal. And then the mass of the remnant, so the mass of the final object, can be measured by the signal. So these are the gravitational balance laws. I am just showing them to you that they have this form. As I was telling you, deriving them is rather cumbersome and a bit complicated and lengthy, but they have to have this very specific form. You have the left-hand side given by the mass and the kick velocity, and then you have the right-hand side. So observe the very close resemblance with the mechanical balance laws and with the gravity balance laws. On the left-hand side, you always have the energy difference between initial and final state of the system. Here, as you can see, is C squared M is the energy of your system between the final and the initial state. And on the right-hand side, you have the total energy lost by the system. So the energy that is carried away by the gravitational waves. So this represents like this derivative of the Lagrangian in the mechanical balance law that we saw. So this is analogous to that. But you can see there is this additional term that we didn't have in the mechanical balance law. And this is a completely new phenomenon, which is relevant and present in general relativity, and is the gravitational wave memory. And it has this very specific form. And so if you have a waveform model that doesn't correctly have this phenomenon of gravitational wave memory, then it will not satisfy correctly your balance laws. Okay, so observe that this memory term is essentially the difference of the two values, h plus and h cross, at distant future and at distant past. And in the distant past, before any gravitational wave has been emitted, you would naively expect, oh, there was no gravitational wave, so the strain should be zero. And also in the distant future, after the gravitational wave has long passed, one should expect that the strain should be zero. And therefore, when you build the difference, you would naively expect that this should be zero. However, general relativity explicitly predicts that the polarization in the distance past and in the distance future can differ from each other and give rise to something non-zero for this memory effect. Okay, so this difference has a very clear interpretation in terms of a ring of test masses. And imagine a gravitational wave passes through a ring of test masses, and as we have seen, they start oscillating. And of course, the proper distance between these test masses is a function of the strain of the gravitational waves. And after the wave has passed, one would expect that the strain is zero, and therefore that the original ring configuration would go back to its original configuration. However, GR, as I said, predicts that in general, the h plus h cross after the passage of the wave is actually non-zero. So this means that the proper distance between the test masses is permanently changed, and this means that the shape is permanently shaped, and this would mean that gravitational wave memory effect is a prediction of general relativity that gravitational waves gives rise to a permanent displacement of test masses. Here you can see when such a wave passes through a ring of test masses, once the gravitational wave passes, there is a permanent deformation. Okay, so the ring configuration is very different after the wave has passed. And in the waveform model, you see that there is this shift in the amplitude here, which is raised. And so instead of going to the initial starting point where it started, it has this permanent deformation. Okay, so I am here showing you like a very simple waveform model. This is a completely analytical gravitational waveform model, actually for undergraduates, which is very nice. So you can take this and play with this waveform model. So we assume that there are these two objects with masses m1 and m2, some zero initial spin. They orbit with each other with a time-dependent separation r of t, and they have time-dependent orbital frequency, and you can analytically find concrete analytical solutions for the inspiring phase of the waveform. And for the numerical relativity, you can make a numerical fit to numerical simulations in terms of amplitude and phase, what has been done in this paper. And so then the inspiring and the merger ring down waveforms are then matched into a single analytical waveform. Here I am plotting the waveform model that you get if you follow this example in the paper. And now the idea would be we would take this concrete solution. So we take this waveform here, which is given analytically, and then we plug this into our balance law and then check how good it does the job. So on the left-hand side, since in this model there was no kick velocity, it's given just in terms of this formula with kick velocity being 0. And on the right-hand side, they also didn't have any memory in this waveform model. So it's just simply given by this basically simplified version of the balance laws. And then we can then plug in our very specific strain, analytical strain. And here I am plotting the radiated power in order to compute basically the right-hand side. And as you can see, here you get a specific value for this right-hand side. And then for the left-hand side, I have taken as an example the first ever measured gravitational wave. And it gives you a very concrete number. And now you can compare this concrete number from the left-hand side with this concrete number for the right-hand side. And if there is a mismatch, you have then a way of knowing by how much error your approximated model is making. Okay, summary. So using balance laws, we can compare and improve waveform models, determine which model performs better in which region of parameter space, and that finishes my summary. I'm very sorry if it took longer than I was supposed to. So I'm happy to take any questions.
Thanks, Lavinia, for your wonderful talk. So there are a few questions. People have raised their hands.
Yes.
So there is a question from Shailesh Kumar. Shailesh, can you ask your question?
Yes. So thanks for the nice talk. So I have I wanted to seek a clarification. Actually, in one of the slides, you depicted a figure where you had a energy influx that is E in and energy outflux E out. So I was just I had a confusion that what is the source of this E in, that in energy flux, and E out, if I'm wrong or right, just correct me, that so if you have a binary system, so if one object is inspiraling the another object, so ultimately as a back reaction, there'll be generation of the gravitational field, that is GW flux basically we can say, and this GW flux ultimately will travel towards the infinity, or you can say that
Recording stopped.
Earth, right? So this E out, that energy outflux, is the one that is traveling towards the infinity. Is that the one that is coming from?
Yes.
I see. Okay. So this is like
so basically
energy flux.
The energy outflux in the GR case is exactly the energy carried away by your gravitational waves.
Exactly.
So
and this, what is? Yes, please.
And so in the case of the mechanical balance laws, imagine you have these two systems. This energy could be, I don't know, maybe because you are heating up the system. You are increasing the temperature, you are giving some energy into your system.
So
and the energy out.
This E in, that energy influx, does it source independent, or it depends on if you are giving some external energy to the binary system? So this E in depends on
this would be, for example, in the case of the gravitational waves, this would be the energy. Basically, we know from special relativity that Cm squared is basically energy, right? Energy of having mass, and therefore the initial energy is simply given in terms of, let me just show you the balance law again. Therefore, E initial is basically c squared m, and m is the initial mass of your binary.
Right. I understand this. Yes.
And the energy outflux is basically exactly given by the gravitational waves that carries out energy from your system to the far infinity.
Okay. So one clarification, basically, that suppose if you take a background, suppose if you have a deformed Kerr geometry or any black hole, modified gravity black hole solution, if you take, and if we in fact do the leading order post-Newtonian analysis, so this procedure will follow through, right? This balance law.
Yeah, you have to be very careful, because when you change gravity, the form of this balance law,
Right.
these expressions of the balance laws will be changed dramatically depending on what gravity theory you have. So, I simply have given you the form of this waveform, but to really derive it from your gravity theory is really very, very complicated thing. So I think I had here put the reference here. Even in GR, to get this nice balance law is not something like easy peasy. You need to do a little bit of work. And as soon as you change your gravity theory, your balance law, the expression of your balance law here will change. The way how it depends, for example, of m, of kick velocity, or maybe additional parameters, the way how h and its evolution depends, this will all change in this expression, yeah.
But at the 0 PN, that zero relativistic post-Newtonian order, this should be invariant, or there could be 0 PN if we have some deformation, suppose. And also this will, in the 0 PN, we can get some deformation if it is possible given a background or the theory we are taking, right? So this expressions basically they at the 0 PN should remain invariant, or they will also change?
Yeah, it depends. I guess if you assume that your non-GR theory introduces only in the very highly nonlinear regime some new effects, and that actually in the post-Newtonian approximation regime that is very close to GR, you can expect that the balance laws are going to be very similar. But here, this expression is really valid from t minus infinity to plus infinity. So you would probably need to cut your integral to a point where your inspiring phase stops.
That's right.
Yeah. But if you make this assumption that your non-GR effects are highly in the nonlinear regime and not in the inspiring phase, then the balance laws will be probably the same, and they will be changed only in the highly nonlinear regime. Yeah.
Yes.
Okay.
But the highly nonlinear. Okay.
So let other people also ask the question.
Yeah. Sure. Yeah. Sorry. Yeah.
So
if you have more questions, feel free to write me.
Yeah. Sure. I'll get in touch with it. Thanks.
Okay. So Indranil Chakraborty, do you have questions?
Yeah. Hi. So thanks for such a nice introduction to this topic. So what am I confused about is this the balance laws that you mentioned. So can we find out the gravitational memory for this, or we can check whether the gravitational memory is implemented in the waveform model?
So yeah, imagine you have a gravitational wave model which doesn't have the memory in it, and then now you take it and you observe it, and then you compare it to this balance laws. Then you will see that your left-hand side gives you a different number than the right-hand side, because the right-hand side actually explicitly contains the memory contribution. So, in other words, your observed gravitational waves that actually has in it the memory effect, but your model is somehow missing it, then this balance laws would be a way of telling you that you are missing very important physics.
Yeah, but that doesn't calculate the gravitational memory, right? Because the H plus and H cross you are taking from a test waveform.
No, but you have to compute this quantity. This is exactly the the contribution of your memory. So if you compute this expression, this is your memory.
Okay, fine. And another question is that does this follow from the bonding mass law situation?
This is one way of I mean, there are different ways of trying to get the balance laws. So, for instance, this is all built on going to far infinity for asymptotically Minkowski spacetimes, and then the symmetries of this asymptotically Minkowski spacetime is given by the BMS group, and then now you use all the techniques available in order to basically compute your energy, the conservation of energy for this asymptotic flat observer, and in this way you derive this balance laws.
Okay, thank you.
Shayantan Ghosh.
Yeah, so I'll just ask a very quick question. It's not a, so I'm saying that the H plus H cross, you have taken the TT gauge, right? So I'm saying that in, say, if I want to check the, say, modified gravity, non-metricity or torsion-based gauge, how to approach the gravitational wave, this calculation? Like, I mean, it is very susceptible to the Levi-Civita connection, right? So I was just wondering that, could you give a direction that how one start fixing the gauge and whether this calculation to pass through if I choose a non-metricity, like a Heisenberg type connection, etc. So that's it.
Yes, that's a very good question, and also a very complicated one, unfortunately. Of course, if you have something like non-metricity based or non-GR theory, then you have this additional connection degree of freedom that will actually contribute to your polarizations. So on top of the H plus H cross, you will have also the polarization contribution coming, let's say, from the connection. And depending on the very specific theory, you will have a different expression. Now, using the whole BMS and this conformal completion approach is more involved. So there are some attempts where people have tried to do that for f of r gravity. But in our recent work, we have tried to use actually the Isaacson approach. And in this Isaacson approach, it's actually very easy to get, for example, the memory contribution. They're using perturbative analysis, and you have to take your equations of the gravitational waves, divide them into the high and low frequency equation, and then compute the cubic order perturbations, average this perturbation, and then compute the back reaction onto your linear equation. And in this way, you can obtain your explicit form of the memory. But like non-perturbative exact balance laws, deriving them, it's way more challenging. And then you would really need to go to this reference that I was giving here, and you would need to do all the step of conformal completion, then the peeling theorem, and all the steps that we do in general relativity, then you would need to do that for this other theory.
Okay, thank you. Actually, I read your review in F2 gravity, actually, so that's what I was wondering, that it is very susceptible to the connection. That's okay. Thank you, ma'am. Very good.
Okay, there are a couple of questions written in the chat box. One is that just like any ordinary wave, could gravitational wave also interfere with each other?
Yes, of course, yes. Just like any electromagnetic or any wave, gravitational wave would also interfere, and you can use this interference in order to get more additional physics, and people are doing that. You can also have gravitational waves that that infer or that pass through different system and have shock waves and whatever. So anything that you can have as a physical effect with the electromagnetic wave, for example, you can also have with the gravitational wave.
Okay. And there's another small question. Would it be possible to apply similar mechanical balance laws for angular momentum in this study?
Yes, absolutely. Yes, there are also the balance laws for angular momentum. Here I only showed the energy conservation, but there is also an equation for the conservation of angular momentum, and this gives you an additional test for your balance laws. Due to time constraints, I didn't show them, but there is also mechanical and also GR balance laws for angular momentum.
And one last question by Shivam Kumar Mishra. He raised his hand. Shivam, you can ask your question.
In like gravitational waves are disturbances in space-time fabric, no? So you've considered energy differences. So what you're saying is when the two black holes are colliding, they are giving their energy to space-time. You are not considering the space-time, the properties of the energy is a property of a body. So you're not considering it independent of the space-time.
I mean, you have two things, right? You have one which is the object themselves, and the objects themselves have energy, right? This was this mc squared, and they might also have additional energies, which we do not consider in this simple case. So just by having these objects, your space-time has the energy mc squared, and anything in that space-time, mass or energy, can give rise to changes of your space-time itself, right? This is the nonlinear GR, so it can source its own evolution, so to say. And then when these two objects evolve, right, they are not just sitting around and just have mc squared, but they also have h dot, which has a time evolution. And this gives rise to this propagation of gravitational wave, and that the system emits the gravitational wave energy. So if you want, the system at far infinity knows that there were these objects which carried the energy, and this system lost energy, and the far infinity observer is measuring this loss of energy through the gravitational waves.
Okay, thanks.
Okay, so let us.
Sorry, Professor Ranjan, can I ask a quick question?
Oh, sure.
Yeah, so I mean, it's related to the question that Indranil asked. So these flux balance laws or balance laws are probably can also be derived from the time derivative of the charges, BMS charges. So the charge expression that contains the stress tensor to the right hand side, and let's say mass and other angular momentum, etc. And one can time derive the expression to get balance laws. So the balance law you are showing are equivalent to those laws?
Yeah, I mean, there are different ways of how you can compute these balance laws. And yes, in principle, it's, as you said, right, you can associate that to the time evolution of involved charges. You can associate that to the properties of symmetries that I was mentioning at far infinity due to the BMS symmetry and so on. And so there are different ways of getting exactly the same balance laws. But at the end of the day, the expressions you get are exactly the same.
Okay. So can there be then this memory effect that you are saying? It's kind of a memory effect that are associated with supertranslation symmetries, and memory effect, you know that some memory effects are also associated with the super rotation, which are spin memory effect. So spin memory effect can also be derived in this way?
Yes, absolutely. Yeah. I haven't even talked about that part. Yes, absolutely. This is a very good question. There can be also spin memory effect. There could be also, if you have another GR, there could be maybe, scalar memory or vector memory, if you have, for example, vector tensor theory, or if you have an additional connection, the connection memory, so to say. and depending on how you try, for example, if you use the Isaacson method, which is like the simplest way of getting that, you can derive then this expression here for the memory with this new effects.
Okay, nice. Thank you for your talk.
Okay, so
thank you.
So let us thank again Lavinia for this wonderful introduction for the gravitational balance laws. So thank you, Lavinia, for
thank you very much for having me
and giving that talk. Yeah, thank you very much. Yeah, over to Srijit.
Yeah. So let me thank you also, Professor Anjan. So now we will be switching to our last speaker, last session of this day 2 of NAR-24. And to conduct this session, I invite my colleague, Dr. Seema Kushwaha. So over to you, Seema.
Okay, thank you, sir. Good evening, everyone. Let's move towards the last session of this evening. So we have the speaker, Dr. Vaisakh Prasad, with us. Good evening, sir.
Hello. Hi, am I audible?
Yes, sir. Yes, sir. You are very much audible. Okay, so I would like to take my opportunity to introduce you, sir. Dr. Prasad is a postdoctoral fellow at the International Center for Theoretical Sciences, Bangalore. He was also a Shyama Prasad Mukherjee Fellow during his PhD at the Inter-University Center for Astronomy and Astrophysics, Pune. His research interest involves understanding the geometry of dynamical horizons and physics of binary black hole mergers using numerical relativity and studying their imprints on gravitational waves. With this introduction, I would request Dr. Prasad to please begin with your talk.
Hi. First of all, thank you very much for this kind introduction.
Recording in progress.
I'm audible and my screen is visible.
Yes, sir. You are audible and the screen is visible.
Okay, and my slides are changing as well.
Yes, sir. Yes, sir. It's
okay, great. Okay. So thank you very much for inviting me to this wonderful workshop. So today I'm here to talk to you about physics of dynamical horizons and their applications to numerical relativity. And what I'm going to talk to you, what I intend to do today is to give you an introduction to what dynamical horizons are. I believe you have already had a nice exposure in one of the previous sessions. And further, to bring about some recent developments in the field, which is exciting and which I'm currently also contributing to. So let's start the talk. The plan of the talk is as follows. In the first part, I will give a brief overview of isolated and dynamical horizons, with particular emphasis on their applications to numerical relativity. Followed by, in the next section, I will describe one of the most important products from numerical relativity simulations, which are gravitational waveforms, which are crucial for detecting signals of binary black hole coalescences. I will also describe briefly the kind of post-processing that is required to prepare the gravitational waveforms which are computed through numerical relativity simulations and make it ready to be used in waveform models. Finally, I would like to spend the next half of the talk, hopefully I'll have that much of time left, in describing some of the recent developments in the field. Okay, onto isolated and dynamical horizons. You might have already heard about these topics, so I'll try to be brief, but please feel free to ask questions if you want me to go slow. Let's imagine a situation. We are now looking at the left-hand side figure. Let's imagine a situation where there is flat Minkowski spacetime. There is no gravitational radiation falling in until a certain instant, which is marked by this line here, wherein a null fluid starts collapsing inwards. And once that happens, of course, it's inevitable that a black hole should form. And after a finite amount of time, suppose the collapse ceases and the space-time becomes stationary or static. What we would expect is that the space-time would have an event horizon, which is described as the boundary of the causal past of future null into infinity, which is exactly this line. So how we would identify this is basically that we wait till all the dynamics ceases, and then we track light rays backwards in time and find out the last light rays that reach from the innermost regions of the space-time to future null infinity. The last light rays which can escape out to future null infinity. And once you start drawing these light rays, you suddenly realize something. What is that? So the very interesting part in this exercise, you realize that the event horizon would actually extend to regions of space-time even before the start of the null fluid collapse, which means you could as well be sitting in a region of space-time which might be engulfed inside a black hole sometime into the future in anticipation of matter or some kind of energy that might fall in. So there might as well be an event horizon that's developing in this room right now. You might have heard this phrase. So this brings up an interesting, troubling aspect of these event horizons, namely that they are teleological in nature. They can form and grow in regions of space-time which can be flat. They can form and grow in response to nothing falling into the space-time. Ideally, we would like to have horizons growing in response to a local flux of energy into the space-time. This is clearly not the case. So right away, we begin to realize that to study dynamical situations, event horizons are probably not useful. There are several other troubling issues about the usual event horizons. Especially suppose we want to study a space-time wherein there is a ring of matter or there is a certain amount of dynamics happening elsewhere away from the black holes, but the black hole itself is not absorbing anything. The black hole itself is static or stationary. Even in that context, the usual way of studying black hole thermodynamics or mechanics is insufficient because of the requirement of global stationarity. We often invoke the presence of a killing vector field, a time-like killing vector field throughout the space-time, and this just seems unnatural because if we are interested in the dynamics of the black hole itself, why do we have to care about what's happening elsewhere? Furthermore, if you look at the first law of black hole thermodynamics, there are quantities like the mass and angular momentum which are defined at infinity, actually. However, the other quantities like the area are defined at the event horizons of black holes. So therefore, you need to go back and forth between two surfaces, and clearly it's not local. Furthermore, there's an ambiguity in the definition of black hole parameters, which means that if there are other objects in the space-time when you want to calculate the mass of the black hole, the ADM formalism cannot be used because intrinsically it will give you the total mass of the space-time. Recently, there has also been research that indicates that event horizons can be non-smooth. They can have creases and they can have corners. Furthermore, it's known that one would require the existence and completeness of future null infinity because of the very definition of the event horizons in order to define them. So given all these issues, it's wonderful that we have learned so much about black holes using the notion of stationary, static space-times and the notion of event horizons. But once we get into dynamical space-time, especially since the successful numerical relativity simulations of 2005 and 6, we need to go farther and we need to employ more sophisticated tools to understand the physics of space-time. So the first idea that I would like to describe today in the context of quasi-local horizons is a non-expanding horizon. And the idea is to basically do away with everything that is global, do away with all aspects of our usual treatment, which refers to things away from the horizon of a black hole, and restrict ourselves to only what's happening at the horizons. And the idea for this originally initiated in Penrose's treatment of the singularity theorem, later on developed by Hayward in the mid-90s, followed by a great systematic development that has happened with regards to Ashtekar, Krishnan, Booth, Fairhurst, and the others. So the first of these ideas is a non-expanding horizon. And the idea is to understand that if you have a horizon which we want to describe as being in equilibrium, then we would want it to be three-dimensional. Cross-sections are space-like, S2 topological spheres. And then there is a null direction, so it's a three-dimensional S2 cross R type of topology. And then we would like to have any of the null normals of this structure delta have a vanishing expansion. What is meant by expansion is basically the fractional change in the area of cross-section of a bundle of light rays that are instantaneously leaving the surface of the horizon. And instantaneously, they can be parallel. Inside this structure delta, you would find that the expansion is negative, meaning that light rays would converge irrespective of what direction you would shine it in, and therefore these regions of space-time are called trapped. So just from these considerations and also certain constraints on the energy condition of the space-time, one can do quite a lot. One can show that if you have such a structure which does not refer to anything at infinity or the future null infinity, you could show that this means that the horizons have a constant area irrespective of the cross-section that you choose. There is a lot more one can do. It so happens that because it's a null topology, it's S2 cross R, the three metric of this surface delta is degenerate. And then, but although it is degenerate, it turns out that by suitably choosing these null normals, one can define a canonical connection, a connection component on delta, such that it can be also treated in the framework of a weakly isolated horizon. And weakly isolated horizon is what is very interesting, because you could start talking about extension of the laws of black hole mechanics to it. So I would not go into the specifics of weakly isolated and isolated horizons, but what I would like to mention is on adapting these structures, on discussing these quasi-local quantities, one can successfully extend the laws of black hole mechanics to fully dynamical scenarios as process laws. And for example, one can recover the fact that the surface gravity of a weakly isolated horizon is constant. And also, this means that one can also describe space-times which have gravitational radiation arbitrarily close to the horizon, but it's not absorbing it, so it is not growing. So irrespective of what's happening in other regions of space-time, one can now discuss in a robust way what happens at the dynamical horizons, at the isolated horizon. Sorry. One interesting consequence, one interesting feature of these isolated horizons is that you can define two sets of numbers called the multipole moments. These are called the source multipole moments. These are very much like the field multipole moments, which are due to Hansen defined at infinity. So these multipole moments are completely defined on the horizons of black holes, and they quantify the horizon geometry in the strong field regime. They quantify the geometrical state of black holes in the strong field regime without reference to what's happening elsewhere. And in this framework, what basically happens is there is the 2 Ricci scalar of the cross sections of the horizon, which basically encodes information about the mass multipole moments. You similarly have spin multipole moment information coming from the extrinsic curvature. And all these are integrals computed on the leaves or the foliations of an isolated horizon. And it turns out that these numbers invariantly characterize the horizon geometry. And given these numbers, you can reconstruct the horizon geometry. And as an example, if you put n equal to 0 for the mass multipole moment, you would recover the familiar mass of a black hole. And for the spin multipole moment, you would recover the spin of the black hole. And in general, for a Schwarzschild black hole, you would have all the spin multipole moments vanishing, but you would, of course, have all but the mass multipole moment vanishing for a Schwarzschild black hole. The situation would be changed for a Kerr black hole, wherein the spin would be non-zero, and all and even n values of the mass multipole moment would be non-zero. Okay. So now I would like to move on to dynamical horizons. And I would also mention this briefly. I would point you to references for more details. So the idea is very simple, is to use the same concept of trapping horizons and extend it to dynamical scenarios. We would still want to look at the surface, which is marginally trapped, marginally outer trapped, actually. So you would have the expansion of the outward pointing null normal to be 0, and inside you would like to have the expansion to be negative. And in this framework, if you track the surface, which is marginally trapped, it turns out that there's a robust way to define the mass and the angular momentum. It has no teleological properties. You could extend the loss of black hole mechanics as process loss. Of course, this would be very useful to study the evolution of black hole horizons in a situation like a binary black hole merger, which is very interesting. And therefore, in this figure on the left-hand side, if you see what is in this gray shaded region is actually the trap region of a space-time, and the boundary of this trap region, which is separating the blue from the gray region, is a dynamical horizon. This dynamical horizon only starts to grow in response to the local flux of radiation that is falling inwards starting from this time. And once these marginally trapped surfaces form, and then they undergo dynamics, and far into the future, once all dynamics ceases, they would asymptote the event horizon of the spacetime. And at this point, the horizon becomes null, which is shown by the top half of the right-hand figure. And in this region, the event horizon would, of course, be coinciding with the isolated horizon of the black hole. Okay, so another interesting a viewpoint to look at is, if you look at one of the simplest solutions of two black holes, which, by the way, are the starting points for constructing initial data for binary black hole simulations. These are called a family of Brill-Lindquist initial data. So if you look at this solution, the geometry is as follows. You basically have a sheet, which is a three-dimensional hypersurface, and embedded in them are two punctures wherein the surfaces of these punctures would represent the black holes, each of the two black holes. And it turns out that because of the nature of the coordinates that were chosen to get these punctures, these have their own free asymptotically flat ends at 2 points. And this is a very special case if you solve the constraint equations with a lot of assumptions, namely moment of time symmetry and no linear momentum and so on. You would recover this solution. And what is interesting is that if you compute the area mass of the spacetime on the top sheet, you would get the total mass of the two black holes. But how would you even compute the individual masses of two black holes? If you imagine in a numerical simulation at an instant of time, you would have two black holes. And how would you do that? If not for these two bottom sheets, there was no way of computing the individual masses of the two black holes. It turns out in this case, because of the simplicity of solution, that using the asymptotically flat ends of the individual punctures, you could actually compute the individual contributions to the masses. But however, in a general numerical simulation, if you stop a numerical simulation, take a snapshot, you would get a hypersurface which is three-dimensional, but you would not have access to these regions because of the complicated dynamical gauge conditions. So it seems that there is no way of computing individual contributions of masses. And this is where the concept of dynamical horizons would be very useful. One would find in a numerical simulation the surfaces which have zero expansions. And by computing certain integrals on these surfaces, one can actually compute the individual masses and the spins of the black holes. Okay, so till now, we have talked about this region of space-time in the strong field regime, but there's of course the most important region of space-time where our detectors are positioned, which is at future null infinity. And I would now like to shift our focus to this region before moving over to discussing some of the recent results in this field. Okay, so here is a picture of a snapshot of the curvature in a binary black hole merger simulation. This is the XY plane. These are two black holes. And these simulations are carried out using Einstein Toolkit. It's an open source finite difference code. And therefore, you see these several levels of mesh refinement, which are required to resolve the finer features of the space-time in strong field regions. So you would see nested refinement levels. Anyway, so I would give a brief overview of the numerical simulations that I ran in order to understand strong field dynamics of black holes. So numerical simulations are very expensive, as you might have heard. If you use, for example, 128 processors, getting a waveform which is barely usable for modeling could take almost 15 days, and each simulation can eat up around 4 to 10 terabytes of space. And there is a lot of processing that's required before one can use the waveforms, which I will now describe. How we would run numerical simulations is you would first choose parameters of initial data to start with. You need initial data to start evolution for any system. And the initial data would include, for example, the individual masses of the black holes and their momenta. And once these are chosen, there's a way to choose them using post-Newtonian theory. Once these are chosen, then the evolution system will take over, will find initial data first. For example, the elliptic solvers would find the first initial data, and then the evolution system would take over and evolve the space-time. And this figure shows, for example, two black holes which start off at the left extreme and the right extremes. This is the centroid of the two black holes, which start merging on quasi-circular orbits and finally conclude into a final black hole at the center. And this is how distance between the two black holes would decrease in time for different mass ratios. And one of the most important things that we get the products of these numerical simulations are gravitation radiation, which is crucial for detection. And how these are computed are that we use a Newman-Penrose formalism, and we project the components of the wild tensor on a suitable choice of null tetrad very far away from the domain of numerical simulation. Why can't we go up to infinity? It turns out that if we use formulations like 3+1, then we, of course, have finite amount of computing resources. So we cannot afford to keep enlarging our domain. At a certain point of time, adding domains, increasing the size of domain would not affect the result so much. It turns out that you can extract waveforms on large enough spheres, which are typically 500 times the distance of 500 times the total mass of the space-time. And that would be sufficient to compute gravitation radiation and extrapolate them by doing perturbative corrections to the waveform. And these corrections are done by basically computing the wild scalar on different spheres of different radii, and then using certain favorable properties of the wild scalars. For example, the peeling properties of wild scalar psi4 should decay as 1 by r as r increases. And if you are not exactly at r equal to infinity, you would have contributions like 1 by r squared, 1 by r cubed. And using data from different spheres, one can discern what is the coefficient of 1 by r. So this process is called extrapolation. And after having extrapolated, one should, of course, do other corrections. This is the extrapolation that I spoke about. There is also a perturbative way to extrapolate. You can assume the space-time inside the domain is a perturbed Kerr black hole, and you can try to extrapolating using that method. And that's also favorable. And once you do extrapolation, of course, they introduce certain changes in your waveforms up to a level of 1%. What you see on your screen is the changes in phase due to extrapolation of the waveform. So these can definitely not be neglected. These would lead to biased models if they were not done. Another aspect to worry about is a center of mass drift in simulations. Due to physical and unphysical reflections at the domains or at the boundaries of the domains, the center of mass of the black holes can drift. And as you can see, the orbits are slowly drifting away to this corner. And these would, of course, introduce certain changes in the modes that were extracted on large spheres, because the spheres remain put. They don't move in a numerical simulation. And these spheres are used to decompose the Weyl scalar into their spin weight -2 modes. And therefore, these would introduce a certain amount of change in the coefficients which have to be corrected for. And these can also be done, and these are related to BMS transformations of waveforms as well. And these also bring in a sub% change in the gravitational phases, which are important. Finally, we would like to integrate out psi4 to get this strain. And it turns out that integration of psi4, which involves 2-time integrations, is not actually straightforward. The reason is because numerical simulations are not, of course, 100% exact. They have certain noises, they have certain departures, small departures, of course, acceptable departures. And these departures at low frequency regimes induce a certain wavy feature, wavy artifact in the waveforms if you naively integrate them using any sophisticated RK techniques, for example, in time domain. So what one would do is either use a notion, what is known as fixed frequency integration. And if you use fixed frequency integration, you can get rid of these oscillations, as you can see in the cyan color here. The magenta one is time integrated naively using RK methods. You could also do energy minimization approach. That's the alternative, and one would recover the same result. And what you see in green is directly is a strain directly computed from psi4 using Cauchy characteristic evolution methods. So we can see that the cyan curve is very, very close to the green curve here. So once you do all these things, we are good to go. We have several waveforms from numerical relativity, which are ready to now be used for waveform modeling. I would like to pause here for a couple of minutes and see if anyone has questions before I move on to the last part of the talk.
Hi, so I have a small question. So when you talk about this integration method, that fixed frequency integration, and why does that give different results compared to the RK code? I mean, what is so special about this?
So what fixed frequency integration does is basically it identifies low frequency noise in the Fourier transformed version of the strain of psi4, and then basically sets that to 0. And once you identify, the hard part is identifying exactly what frequencies constitute the unfavorable frequencies. And once you do that, you can do a spectral integration. Basically, you know that this, you know the differential of sine and cosine, so you know their integrals as well. You can integrate them spectrally, and you can obtain the sine curve without the artifacts.
Yeah, thanks.
Sir, I have a question. So, can you once again explain what is meant by teleological nature of horizon, and why event horizon is teleological and horizon is not teleological?
Okay, sure, I can do that. Let me just head back. Okay, so in short, in order to find out the location of event horizon in a space-time, you need to know the entire dynamics of the space-time infinitely into the future. You need to be sure there's no further dynamics happening, and the final dynamics that happens actually defines the location of the usual event horizon. And here you realize that once you draw the event horizon in your space-time, you realize that event horizons can exist even in those regions where there is no dynamics happening. So in this initial orange region, there was no matter or radiation which is falling in. It was just perfectly Minkowski flat space-time. But because of dynamics that happened later on, a black hole formed, and the space-time has an event horizon, and light rays from this region can therefore not leave this part of the space-time, can never reach future null infinity. So an event horizon exists even in a flat region of space-time. So an event horizon here is appearing because of dynamics that would happen sometime into the future, in anticipation of something that will happen into the future. And this is what is meant by teleological nature of horizon, of event horizons. And dynamical horizons are devoid of this because we have no references to future null infinity in defining them. We are just interested in how null rays behave. We are tracking the surface, which has a zero expansion, and all definitions are quasi-local. I hope that explains the question.
Yeah, yes.
Okay.
Hi, Vaishak. May I ask one small question?
Yes, please.
Yeah, so you mentioned about this garage Hansen multiple moments, etc. So recently there are some attempts to extract near horizon physics from far region, from the horizon multiple moments, etc. So can you, comment what best we can extract from those multiple moment calculation, which perhaps one can only get at the far region, and what those can talk about the nature of the black hole, whether it's spinning, how fast, etc.
Yeah, sure. This is definitely an interesting question. We do not currently know how the field multipole moments are related exactly to the source multipole moments, which are multipole moments of dynamical horizons. But hopefully, in this section of the talk, I do have some aspects of this that I would touch on, and hopefully, your question might be answered there. Could we wait for this section of the talk?
Okay, yeah, sure.
Okay. Okay, so I believe I have how much more time? 25 minutes? 30 minutes?
Yeah, you have almost 30 minutes.
Okay, fine. So let's now discuss some of the recent developments in applications of dynamical horizons to numerical relativity. This is very interesting, as I mentioned, because we are now detecting gravity waves from coalescing binary black holes. We have quite a few of them now. And the success of numerical relativity in 2005 and 6 have enabled us to start asking questions like, how does the strong field dynamics of a binary black hole system behave? Can we understand these dynamics? We, of course, know a lot about what happens at infinity, but can we really probe what's happening in the strong field region? And therefore, there is interest in understanding dynamical horizons, what's happening at the horizons, and how they may be related to what's happening to infinity. So before the advent or the success of numerical simulations, there were speculations about the possible correlations between what happens near the horizon of a black hole in a perturbed spacetime. Let's imagine a single Kerr or a squashy black hole which is perturbed. And in such a situation, there were hints or there were conjectures or expectations that there is some gravitation radiation, definitely that's being absorbed at the perturbed horizon. And there's also a part of the field that leaves the space-time and goes to infinity. And it's possible that the nonlinear regions of space-time which generate these waves majorly are responsible for sourcing both the waves that are falling inside and the waves that are escaping to infinity. And they may be correlated. So this was a conjecture. And there are several works, there are a couple of works in literature which conjectured the existence of such a correlation in perturbed scenarios in, for example, head-on merger situations, and also quite recently in a binary black hole merger scenario. So what you see on the bottom plot is the flux of gravitational radiation that is computed at infinity, and the flux which is being absorbed in the post-merger phase of a binary black hole merger. And qualitatively, they seem to look similar. So the interesting question to ask is there a correlation between what's happening at the horizon and what we get at infinity? And this is a big deal. Why? Because if you look at this plot, this is actually a cartoon. Please don't take this very seriously. This is like a Penrose diagram, but not exactly, but it illustrates the point. You have the event horizon forming due to the final black hole, which is asymptoting to equilibrium here. And the progenitor of this final black hole is, of course, a binary black hole merger scenario. You have two black holes, the dynamical horizons are shown here. They are revolving around each other and then slowly contracting and merging here, where a final common horizon is formed, which asymptotes to equilibrium. And the event horizon would basically tell you the region of space-time from which no light can escape to infinity. And you immediately see that dynamical horizons live inside event horizons, so they have no causal connection to what happens at infinity. So the question is very interesting as with regards to correlation, because this region cannot send signals to detectors here. So how do we even probe physics here? And then some of the work that I've been doing in the past few years is to address this question. And what I did during my PhD was to understand not only in the post-merger dynamics, but to understand if there are correlations between physics in the in-spiral phase of binary black hole mergers, in the merger and the ring-down phases, and how do we relate these two, for instance. So the work that I'm going to describe now is mentioned here. Please look at it for more details. So system emits gravitational waves during in spiral. A part of it falls into the horizon, part of it escapes to infinity, but it's all very complicated. You have two black holes in spiraling. And then can we expect correlations in the in spiral as well? The goal is to understand this correlation. And in the dynamical horizon formalism, there is actually an exact expression for the amount of energy that's being absorbed due to gravitational radiation at the dynamical horizons in the strong field regime. This is completely covariant in nature. And one of the major contributions is from the shear of the dynamical horizon. Shear is what it geometrically is, a Newman-Penrose scalar, and it contains certain transverse traceless projection of the derivatives of the null normal. And this has a resemblance to the gravitational energy that's being escaping to infinity, and that involves the integral of the News function. So what I did in this work is to compute the shears at the dynamical horizons of each of the two black holes in the in spiral, and also the common dynamical horizon in the post-merger phase, and then see if they are interesting, first of all, and secondly, if these are correlated in any way to the waveform that we receive at infinity. So here is a result. So what is shown in blue is the News function received at infinity, which is computed from the numerical simulation. And what you see in orange is the shear on one of the two dynamical horizons in the in spiral phase of a binary black hole merger. And as you can see, once you align them suitably by a time shift and a phase shift, they seem to agree excellently. The shear seems to have a familiar chirp-like behavior, which means it has increasing frequency and amplitude, much like the gravitational waveform, and they go hand in hand, in fact, all the way up to the merger. There is some deviation in the amplitude fall-off, which we associate with the inaccuracies in the computations of the shear. But however, as you can see, the phase is matching very well. And these were done for a handful of binary black hole mergers with different mass ratios. And we showed that one can recover the parameters of the system using not the News or the strain, but actually the shear at the dynamical horizon. And the match between them are quite good. They are above 96%. Furthermore, we also found that one can, in fact, compute in an approximate phenomenological fashion the shear of the two dynamical horizon using just the News of gravitational radiation, which means you can do this without even running a numerical simulation. So these relations are very interesting because this offers one of the first ways to probe the strong field dynamics of black holes in full nonlinear general relativity. It's a surprising relation, and it would possibly allow us to improve, for example, our current waveform models and carry out tests of GR. And now I would like to also explain how this relation plays out in the post-merger phase of binary black hole mergers. And as you may all know from black hole perturbation theory, the perturbation theory says that if you're treating linear perturbations, if you're trying to solve for linear perturbations of a black hole, then you have quasi-normal modes, you have damped sinusoids. But however, in a binary black hole merger situation, as you may have seen in today's talk by Prayush, that once two black holes come very close to each other, a common horizon forms which is highly distorted. It's very far from what an equilibrium curve black hole looks like. So the dynamics is highly nonlinear. But what we try to understand is it possible to describe the dynamics of this remnant of the common horizon that is formed using quasi-normal modes, which, because it comes from linear perturbation theory, how well does it agree with the theory of quasi-normal modes, and how well does the correlation between the news and the shear continue to hold in the ring down phase? And here is a sample result from such an exercise. What is shown in blue is again the news in the post-merger phase, and what is shown in orange is the shear at the common dynamical horizon. And they have also been suitably time shifted and aligned because the news takes certain time to reach the extraction sphere and the horizon is in the interior. So once you do all that, you see that the phasing of the two agree very well, and the slope of this, the decay pattern, agrees quite well with the dominant quasi-normal mode. What you see on the right-hand side is a numerical noise floor. All numerical simulations have limitations, and on increasing the resolution of the runs, the noise floors would be expected to decrease further and further. And of course, we could find a similar relation between the shear and the news in the post-merger phase as well. Another interesting consequence of this exercise was that you could recover the spin of the final black hole formed using the shear at the dynamical horizon by just carrying out a similar template-based parameter estimation or a best match kind of an exercise and feeding in not the gravitational wave strain at infinity, but the shear at the horizons. You could, in fact, we also showed that you could recover the individual masses of the parent non-spinning binary black holes that led to this common horizon. Okay, so I would again pause here for a couple of minutes before moving on to the last part of my talk. Are there any questions at this stage?
There's a question in the chat actually. I think Siddharth is asking, are there any other ways to visualize and understand dynamical horizons? I mean, without more technical terms.
Okay, so we can discuss about this. I've been working on certain visualizations. Maybe they could help. I will show one of them here. Maybe you could write to me and we can discuss about it.
Okay.
Thanks for the question.
Yeah, there are no other questions right now, so you can go.
Okay, now I would like to move on to another aspect, another problem which I've been trying to investigate in the past few years, which is in connection with tidal deformations of black holes. You all may have heard that non-spinning black holes do not deform. And what we wanted to do in this line of investigation was to propose an alternative formalism, an alternative approach to the problem of tidal deformations of black holes using not the gravitational field at infinity, which is what is usually done, but using actually the geometry of the dynamical horizons. And details can be found in this paper. Please feel free to look it up. So the system is same as the previous case. We have a binary black hole system, two black holes. This particular one is asymmetric. It's non-spinning. Mass ratio was about 0.6. And this is a top view. Gravitation radiation is visualized here. You see nice lobes of quadrupolar, dominant quadrupolar pattern. And the question is, of course, the two black holes deform. These are non-spinning black holes. So the field approach, the field treatment would imply that they don't deform. But what we want to ask is, do the horizons of the black hole deform? And can we associate any strong field of numbers to the deformability of these black holes if they do deform. And the deformation would happen because of the mutual influence that these two have on each other. So the present treatment of tidal deformation, of course, has taught us a lot. The perturbation theory of black holes has taught us a lot. However, they have their own limitations. They cannot be applied in scenarios like binary black hole mergers when the two black holes are very close to each other. Why? Because when the two black holes are very close to each other, they start moving fast. They could approach up to 60% of the speed of light. They come into mutual strong field regions, which means you can no longer associate an asymptotically flat region to each of the two black holes. In order to do a perturbative study, you need to have access to the asymptotic regions of each black hole. You need to be able to differentiate between the contribution of gravitational field of first black hole and the second black hole to the total field at infinity. Such a treatment becomes impossible when the two black holes close in. There are also discussions currently happening on whether the results on the field tidal love numbers are gauge invariant and so on. So these are interesting investigations that are happening. So we wanted to propose and we wanted to find an alternative approach to understanding tidal deformations, which would be valid even in strong field regions, in highly dynamical regions where you cannot asymptote the asymptotic fields of each black hole. And we want to do this using dynamical horizons. And how we do this is using the source multipole moments. Remember, we talked about source multipole moments. There are two sets of numbers, mass, which is shown here, and spin, which is not shown here. These mass multipole moments characterize the geometry, the state of geometry of dynamical horizons. And these integrals are carried out on the leaves or the foliations of dynamical horizon. So this is a three-dimensional dynamical horizon. This is space-like. It has a time-like normal. So it's a one-way membrane. You can only enter it. You cannot leave it. It has a space-like tangent. And then the normal to this space-like tangent is, of course, topological spheres, which would represent instantaneous horizons of black holes in a numerical simulation. So in a numerical simulation, you would have a three-dimensional Cauchy slice, which I have not drawn here. You could imagine that to be a flat sheet. And that would intersect with this three-dimensional tube in a two-sphere, which is labeled by S. And each of these would represent apparent horizons of the black holes, the instantaneous horizons of a black holes. And on these surfaces, if you compute the expansion of the outgoing null vector, they would be zero. And the expansion inside this surface would be negative, meaning that all closed surfaces inside would be trapped. Of course, at late times, you would imagine when there's no dynamics happening, it would asymptote to an isolated horizons where the tangent would be a null vector. So the null vector would be both tangent and normal to the surface. So coming back to the problem of tidal deformations, we would be computing multipole moments on each of these surfaces, leaves S, which represent apparent horizons in a numerical simulations. So we would track the apparent horizon. We would solve a certain elliptic equation at each instant of time in a numerical simulation, find the location of these trapped surfaces, and then compute these multipole moments on each of these trapped surfaces. And why would we do that? We do this because we know what these multipole moments are for an isolated Schwarzschild black hole or a Kerr black hole. Here we are discussing numerical simulations of non-spinning black holes. So it would be apt to compare these numbers with a Schwarzschild black hole. We know what these numbers are for a Schwarzschild black hole. In a numerical simulation, each of the two black holes would be affected by their mutual gravitational interaction. And therefore, the geometry of the horizons would change, leading to a change in these multipole moments. And this is the starting point. Using these multipole moments, which are dynamical, by the way, because each Cauchy slice would intersect one such leaf, S, one such apparent horizon. And as time proceeds, we would get different intersections and they would represent dynamical state of the horizon at each point. So therefore, these multipole moments would also evolve with time. And then by comparing these multipole moments to what an isolated spot shield black hole would have, we can quantify the deformations of the horizon. And these deformations, we showed that can be expanded in simple in a simple expansion, much like a Taylor expansion involving the parameters of the binary black hole system. Here, MTD and MTF are the masses of the individual black holes in the inspiral phase, tidally deformed, and the one that is sourcing the tidal field. So this expansion can be carried out for each of the two black holes. There are two different dynamic horizons, and D is the distance of separation between them. Since these are the only parameters in the system, you would expect the coefficients which are accompanying them to be dimensionless and scaled out. And by running numerical simulations, tracking apparent horizons, computing these multipoles, and calculating these numbers, we aim to quantify the tidal deformability of black holes. And these could be called as strong field love numbers. So here is a plot of how this model that you see on the screen can be successfully used to explain how black holes deform. So what you see on the screen is the n equal to 2, the quadrupolar deformations of black holes, of one of the two black holes, black hole 1 actually, the one which is more massive, that's plotted on the y-axis. And what's plotted on the x-axis is the distance of separation between the two black holes. The data points in black are computed from numerical data, from numerical relativity. And what is shown in cyan and magenta are two different models, each one involving one particular term in this expansion. The cyan model actually involves a leading order expansion. The expansion goes from 1 to infinity. It's an expansion in 1 by d. So if you think about it, the leading order contribution should be 1 by d cubed because of the tidal fields. And the higher order would be 1 by d power 4. So the cyan model actually stops at 1 by d cubed, but the magenta one also includes 1 by d power 4. So model 1 by d power 4, as you might imagine, would be more useful to explain the behavior of multiple moments, especially when the black holes are close to each other. So simulation would start from here, where the distance of separation is maximum. As the black holes come closer and closer, distance of separation would decrease. So black holes, the quadrupolar deformations of black holes increase as the two black holes coalesce. And these are non-spinning black holes. So this shows that even non-spinning black holes deform. And we could successfully compute these tidal coefficients. The first few tidal coefficients are shown here. And these could be called as a strong field of numbers of black holes. Okay, so given that these deformations were found and that these deformations are interesting, what I attempted to understand was, of course, the connection between these deformations and what happens at infinity. Because immediately when we realize that non-spinning black holes also deform, the next important question to ask would be, would it really affect what we see in our signals? Because we currently assume tidal deformability to be 0. And this work attempts to address this question. It's a very difficult question. So there is some progress, and I would like to briefly mention that. So one realization, of course, that came about was that we should be not restricting ourselves to a single index or axisymmetric deformations of dynamical horizons, because as you can see in this figure, there is nothing axisymmetric about this situation. You have two black holes and the situation is highly non-axisymmetric. You would imagine deformations to have all possible components. So immediately, what I did was to compute certain generalized multipole moments. These multipole moments are defined again on the dynamical horizon, but using a more general basis function adapted to the deformed horizon geometry. The Ricci scalar of the individual slices, leaves of the dynamical horizon are expanded, projected on these bases, and these generalized multipole moments were computed. And as I mentioned earlier, M00 would be the mass. We now have two indices instead of one. And for a Kerr black hole, for instance, M20 would give you something proportional to a square, which is the spin of the black hole. And you could also equivalently define the spin multipoles with two indices, and J10 would give you the spin. And these would capture the most general deformations that a dynamical horizon could have. And on running numerical simulations and computing these general deformations, what I found was on your screen, the dominant contribution, what we were looking at before in the previous part of the talk was the L2M0 component. Remember, we didn't have the M in indices. It is still a quadrupolar deformation, but it is an axisymmetric component of the quadrupolar deformation. It turns out there are a host of other contributions, and the dominant one is actually L2M2, which is shown here. And these are oscillatory in nature because they are complex. And as you may imagine, with time, their strength increases as the two black holes come closer and closer to merge. There are different contributions to deformations of dynamical horizons, and they all increase in strength with time. And some of them remain zero, of course, because of symmetry consideration. If you have a non-spinning system and you have the system remaining on the equatorial plane, then there's a reflection symmetry with plus z and minus z. Numerical simulations don't assume any symmetry. So therefore, you have certain noise instead of any data, and certain multipole moments would be zero. And here is a visualization of the deformed state of dynamical horizons in the due process of a merger. And I would like to show you a short video. I suppose I'll have to stop sharing and resume a different screen. Let me try that. Okay. Can you see the video in the background?
Yes. Yeah.
Okay. So these are the apparent horizons of the black holes, which are basically cross sections of a dynamical horizon. And what is plotted on them are the components of the two-dimensional Ricci scalars, which inform us about their tidal deformative state. And I will now play the animation. And as you can see, I'm going to pause him here. So as you can see, the region which is red is actually along the line joining the two black holes. And therefore, this tells us that hole 1 induces most deformation, which is facing it. And this pattern actually follows the evolution or the binary, the orbital evolution of the system. The gravitational waveform from the system is plotted below. And as time goes on, the deformations increase due to the intensity of the colors, as you can see here, before they would finally merge to form a single horizon. Okay. Going back to the presentation. What you see on the screen is a snapshot from the same movie. So the two black holes deform each other, and you can clearly see the L2M2 dominant quadrupolar pattern. And now coming to correlations, it was interestingly found that these deformations, which are plotted in cyan, the dominant component, are also strongly correlated with the news of gravitation radiation, which is escaping to infinity. And this is very interesting again, because the dynamical horizons are causally disconnected from observations. We now know that dynamical horizons deform. So if there is any hope of understanding how our waveform models could benefit from this, this could be a first step. This shows that these are correlated, and there is a strong reason to pursue the effect of these deformations on the observed gravitational waveforms. And interestingly, there were some other results that were found, namely that the qualitative details of the dynamics of the binary black hole system are imprinted on the horizons of the black holes. What is shown in red line is basically the innermost stable circular orbit, the approximate location of it, computed from resummed Hamiltonian. And what you see plotted here are the multipole moments very close to that location, and very close in the neighborhood of this location of ISCO, you would see that there is a sharp change in the growth rate of these multipole moments. And some of the deformations, which were very small, also pick up. So black holes seem to gain hair as binary black hole merger proceeds. They gain more and more deformations. And finally, you could also compute them on the common horizons of the two black holes, and it was found that there is a quasi-normal behavior in how the multipole moments or the deformative state of the common horizon decays with time. And therefore, whatever gravitational hairs that the system gained in the in-spiral phase are actually lost in the post-merger phase, because in the beginning we start off with, if you start off with two black holes which are infinitely separated, they would be non-deformed. They are symmetric. And then finally, you have a final curve black hole, which is also not deformed. In between, there's a lot of gravitational hair that it gains. And in the end, in the common horizon, those gravitational hairs are lost by absorbing gravitational radiation. Dynamical horizons absorb gravitational radiation, losing their hairs. So this leads to an interesting refinement of the hypothesis or the conjecture that there are correlations between strong field and the weak field regimes. Possibly the full multipolar structure of the dynamical horizons could be correlated with that of the Bondi flux at future null infinity. I would also like to mention some other interesting results, which possibly will be talked about in tomorrow's session. For example, quasi-normal behavior in head-on collisions have also been found with overtones, and also certain nonlinearities in head-on collisions have also been found at the horizons quite recently. So there are a lot of interesting physics that one could extract using dynamical horizons. I will now come to the summary of my talk. Black holes are certainly one of the most interesting and important sources of gravitational waves. Recent progress in numerical relativity has enabled us to start probing the strong field dynamics to understand how black holes really evolve, and dynamical horizons are very useful for that. Quasi-local horizons, and with quasi-local horizons and numerical relativity, one would be equipped to study the dynamics in the strong field regimes of black holes. Recent developments have shown that the strong field dynamics is strongly correlated with the weak field dynamics in all three phases of a binary black hole merger. So we could think of probing the strong field dynamics and possibly doing tests of GR. And importantly, non-spinning black holes also tidally deform, and gravitational waves from such systems can carry their imprint. These deformations can be predicted using phenomenological relations. So the multipole moments could be computed using the news because of the correlations using certain phenomenological relations we have. Finally, there is also evidence of quasi-normal structure at the dynamical horizons, even though they may be in a highly deformed state where we would not normally think of applying linear perturbation theory. And there have also been evidences of non-linearities that have been found. So I'll stop here. Thank you.
Thank you very much, sir, for such a nice talk. And I ask the participant, please ask if you have any question. Shiji sir, you are there, you may please ask.
Recording stopped.
Hi, Vaishak. Hello.
Hi.
Oh, I have one quick question. It is about that the flux balance law, where you also have the zeta term as well, right? So apart from the shear, that term is, as far as I remember, is kind of a gauge, right? It depends on the choice of foliation. So, but you have not taken that term into account. So how do you intend to fix that? This term zeta?
Yeah, thanks for the question. So yes, there are two terms in the flux law at the dynamical horizon, and it turns out that the major contribution comes from the shear term, which is sigma. We computed this numerically, And if you have a non-spinning black hole, then this would be of no significance at all. We mostly studied non-spinning black holes. When black holes are spinning, also this would be the dominant contribution.
But that also depends on the choice of foliation you take, right? Even if the choice is spherical.
Yes, because dynamical horizons inherently come with a choice of foliation. Yes, that's true. Although the qualitative details and the relations remain the same, the quantitative, there might be some quantitative differences.
Okay, and there is one more question about this, that it seems that the marginally trapped tubes are most seen are not supposed to be the boundary of the black hole, right? The event horizons are supposed to be the boundary of black hole, right? So, but it seems that there is a tight correlation between what you see on the boundary and what you get at Sky Plus, the graphs that you showed. So why does this happen? I mean, it's not supposed to happen, right? So why should this work at all?
True. We were quite surprised as well to find these correlations, especially in the in-spiral phase. Let me go back to the plot, maybe. Yes. So we didn't expect this to hold in the in-spiral phase, and it was quite surprising. And I have spent some time thinking about it, but I don't have a good explanation of why this is happening, why there is such a nice correlation in the in-spiral. For the post-merger phase, one could come up with some intuitive explanation. I should say that intuitive explanation was built after I found some of the results in the post-merger phase as well. And that intuitive explanation is basically that if you have a single black hole, then possibly there is a region of space-time from which most of the gravitational waves are being sourced because of the non-linearities. And the same source is responsible for feeding energy into the black hole and to infinity. And probably there are correlations. It's very loose, but there is some intuitive picture. But in the in-spiral phase, we have no idea. This is an open question, of course. And because these are completely nonlinear simulations, it becomes very difficult to attack this problem using analytical techniques.
Oh, okay. Thank you very much.
Any other question, please? So there is one question in the chat box.
Yes.
Like, are there any other ways to visualize and understand dynamical horizons? They are asking about without more technical terms. Another way without more technical terms to visualize horizons.
So one can think of dynamical horizons as in a similar way as we think loosely of the usual event horizons, in that inside a dynamical horizon, everything remains trapped. So if you suppose you bring in a laser which can shoot parallel rays of light. If you bring in that laser and you stand here in the outside regions of space-time, if you shine the laser, you would realize that the cross-sectional area of the light beam that is being generated increases in area with time, irrespective of which direction that you would shoot in. However, inside a black hole, if you move in this trapped region, you would see that irrespective of what direction you shoot the light rays in, they always tend to converge. And this is captured in the idea of trapped surfaces. And these trapped surfaces are two-dimensional and closed. If you take any sphere in this four-dimensional region of space-time, you would find that all surfaces would be trapped, meaning you would eventually head into a singularity. And then if you have a region which is trapped and a region which is untrapped, definitely there should be a boundary to that. And that boundary is what a dynamical horizon is. And that boundary is a marginally trapped tube. So it's a three-dimensional boundary because we are discussing boundary of four-dimensional space-time regions. So the codimension would be one. And this surface would have instantaneously parallel rays of light. Light rays would neither converge or diverge, very loosely speaking. And therefore, in a dynamical situation, it would be very appropriate to use dynamical horizons to describe as surfaces of black holes instead of the usual event horizons. What event horizons would give is basically, if you want to understand what region of space-time can you have light rays escaping to infinity, then you can discuss event horizons. But if you want to ask what would you call as a surface of a dynamical black hole, it would be more apt to use dynamical horizon. I hope this was better. This helped your question.
I hope that participant got the answer.
Yeah.
Srijit, you have?
Thanks for the answer.
Okay, yeah.
Okay, may I ask one question? So I am coming back to the question that I asked earlier. Anyway, so I mean, little refined one now. So I mean, there are some proposals that are made by, I think, Abhay Badri, etc. That to relate late time. The dynamical horizons eventually will ultimately tend to the event horizon. So at late time, how to get the correlation between the Scry plus and this event horizon, which the dynamical horizon eventually set up to. So then one can perhaps do some slices like hyperbolic slices, which probably connect the dynamical horizon and the event horizon initially, and then you give data, do numerical relativity simulation, and then the hope is that at the final, at a very late time, the slice will contain a car-like solution plus some perturbations, quasi-normal mode perturbations. So these are the proposals that probably for last 1 or 2 years, Abhay and others are making. So has there been any progress on this? I don't know. I mean,
Yes, certainly. Thanks for the question. Sorry, I think I had to sort of keep a track of time, so I may have gone a little too fast. So this plot, which I showed on the deformative state of the final black hole, precisely attempts to address that question. It does not use hyperboloidal formulations, of course. It still uses 3 plus 1. But what this shows is that the final black hole, the final common horizon, is asymptoting a Kerr horizon modulo numerical noise. What you see here is that the multipole moments which encode the deformative state approach the Kerr multipole moments. After a certain amount of time, they are just numerical noise data. This is the numerical noise floor for the L2M1 and L1M1 modes, whereas this is the numerical noise floor, which is not too low, but it is still lower than the dominant multipoles for the other two multipoles. And what this shows is precisely that we have a common horizon that is settling down to a Kerr horizon. And we have understood this, of course, but even in this situation, I of course also have to add that the decay rate of these multipole moments were found to be consistent with the quasi-normal modes, the dominant quasi-normal modes. And what is shown in cyan here is actually the L2M0 mode, and the Kerr black hole has this to be non-zero. Using the spin of the final remnant, this could be computed theoretically, and the green dotted dashed line shows the numerical computation, and they seem to agree well, which means that the black hole is settling down to a Kerr black hole. But there's another part of your question which is still open. Of course, it's a difficult problem. How do we connect these source multipole moments of a Kerr isolated black hole with the field multipole moments, for example? And that is still an open question. And that question stands even in the absence of any dynamics. So this is really an open question. And with regards to the question I just discussed, I have a reference. Yes. So the figure I just discussed can be found in this reference, and possibly further details if you'd like to look it up. Did that at least partially answer your question?
I think Srijit sir got disconnected for a while.
I see.
I think, I got disconnected. Let us conclude this session, so I may talk to you after this meeting or somewhere in detail. I could understand that in your own work, this question was addressed in some way, but without using hyperbolic slicing.
Without using hyperbolic slices, even if we use hyperbolic slices, numerically at the level of correlations, we could understand how they may be correlated, but in order to compute, for example, the source multipole moments using the field multipole moments or vice versa, I think we are still a long way from that.
But there was some doubts over that. Introducing the car data in an invariant way initially. So I don't understand that thing very clearly. So to have this, yeah.
Please
okay,
share
thanks, Vaishak. And I thank also the chair for this session, Seema. And so we conclude this day 2 of NAR-24. And tomorrow we will start early at 9 a.m. IST for a talk on machine learning with Mathematica. So hope to see you all tomorrow, and bye-bye for now. Thank you.
Thank you, sir.
Thank you. Thank you.